Around 470 million years ago, our planet resembled a vast aquatic realm. This wasn't the familiar setup of oceans like the Atlantic or Pacific, or seas such as the Mediterranean and Caribbean, with steadfast continents resisting the tides. Instead, the Ordovician Earth lay submerged. Global sea levels towered 600 meters above today's, a change that devastated terrestrial landscapes. Inland seas had encroached upon continental hearts, flooding plains and basins, transforming potential firm Earth into boundless stretches of sun-warmed, illuminated waters. Viewed from space, the world appeared strikingly otherworldly. The northern hemisphere consisted almost wholly of ocean, an immense azure void, interrupted solely by isolated island chains and sporadic volcanic summits. In the south, land featured more prominently, yet even the supercontinent Gondwana, which would later fragment into Africa, South America, Antarctica, Australia, and India, remained partly inundated, its edges submerged and its core dissected by waterways linking remote coastlines. The continents we recognize today were absent. North America took the form of Laurentia, a stable craton positioned across the equator and tilted 45 degrees from its current alignment, nearly completely submerged. Europe manifested as Baltica, wandering through southern tropical latitudes, divided from Laurentia by the Iapetus Ocean, a seaway destined to vanish over the ensuing 200 million years. Its closure, forging the Appalachian Range alongside Scotland's and Scandinavia's highlands. Siberia drifted independently in the northern seas. China comprised fragmented blocks, petite continental fragments not yet united into their present form. The layout felt utterly foreign. Conditions were intensely harsh. At the period's outset, carbon dioxide in the atmosphere hit 7,000 parts per million, a figure that demands perspective. Today's CO2 sits at roughly 420 parts per million, a level already driving planetary warming, ice sheet melt, and rising oceans. The Ordovician atmosphere carried almost 17 times that amount of the gas. The resulting greenhouse forcing dominated utterly. Tropical ocean surfaces likely surpassed 45 degrees Celsius or 113 degrees Fahrenheit. Contemporary coral ecosystems suffer bleaching and mortality from just a couple of degrees increase over baseline. The Ordovician tropics represented a thermal frontier, a realm survivable only by adapted species, where the seas push the boundaries of endurance for intricate life forms. Polar regions lacked any ice. Glaciers, ice sheets, and frozen waters were non-existent. Equatorial heat extended poleward, softening latitudinal temperature contrasts and yielding a planet free from the distinct climate bands we see now. The region destined to become Antarctica, part of Gondwana, enjoyed mild, possibly balmy weather, its coastlines bathed in waters that might feel inviting to today's bathers. This constituted a hothouse Earth, among the hottest phases in the last 500 million years. Life forms had previously acclimated to such warmth and would do so once more. The creatures of the Ordovician had not evolved in torment. They arose amid these extremes. Their biological processes were calibrated for heat levels that would prove fatal to their latter-day relatives. What strikes us as severe was routine for them, but the swelter proved temporary. Midway through the epoch, environmental patterns started evolving. CO2 concentrations fell from 7,000 to around 4,000 parts per million. Explanations for this vary among experts. Diminished volcanic output might have curbed CO2 releases. Accelerated erosion of freshly elevated ranges could have sequestered atmospheric carbon, or early terrestrial vegetation, in its initial forays onto land masses, might have begun influencing the balance through carbon fixation and boosted mineral breakdown. Regardless of the driver, the chill set in. Mid-Ordovician eras grew milder than the initial ones. The later stages turned even cooler. Those inland seas proved pivotal to it all. When seawater overruns continental expanses, it fosters remarkable environments. Depths stayed modest, dozens of meters, not kilometers, allowing sunlight to reach the seabed. Fertile sediments flowed from nearby exposed terrains. The ocean floor evolved into a thriving ecosystem, a foundation for attachment, construction, and proliferation. These vast inland waters spanned enormous areas. Picture the Mediterranean expanded to blanket North America's heartland, or the Caribbean overlaying the Sahara Desert. The magnitude defied easy grasp. They offered millions of square kilometers of temperate, nutrient-rich, brightly lit seafloor, exceeding the extent on present-day Earth, surpassing Cambrian precedents, and possibly outstripping anything to come. The life that populated these waters descended from the Cambrian burst of diversity, 50 million years prior. Animal phyla had proliferated at an extraordinary pace, generating the core designs that endure into our time. Arthropods, mollusks, echinoderms, brachiopods, chordates. The core designs of animal life emerged during that initial burst of evolution. The Ordovician era brought a fresh approach. It expanded those designs exponentially. No fresh phyla this time, but an explosion of classes, orders, families, genera, and species. The Cambrian sketched the plans. The Ordovician constructed the metropolis. Diversity among marine animals nearly tripled over this span. Family counts surged from about 100 to almost 500. All principal marine invertebrate lineages proliferated, occupying habitats untouched by the Cambrian. Brachiopods evolved into varieties that would command ocean bottoms for the following 200 million years. Bryozoans emerged anew, their communal structures injecting added intricacy into reef communities. Cephalopods expanded in size, turned fierce, and ascended to top predators of the era. Trilobites, already varied, grew even more so, developing odd spines, massive eyes, and forms suited for swimming, digging, preying, or evading. Researchers label this the Great Ordovician Biodiversification Event, or GOBE. The phrase gained official status in the 1990s through a global collaboration of paleontologists who cataloged the transformations. The GOBE wasn't one isolated incident or instant, but a prolonged expansion, enduring tens of millions of years. It stemmed from endless adaptive trials playing out in the submerged landscapes. The Cambrian explosion grabs headlines. The GOBE stays obscure. That's a flaw in mainstream science, since for raw spikes in variety, novel shapes, and oceanic revamps, the Ordovician surge outpaced it. The Cambrian crafted the essentials. The Ordovician revealed their potential. The fellow who coined the era's name sought to halt a conflict. Charles Lapworth, a Scottish educator who pivoted to geology, labored in Welsh Highlands during the 1870s. He landed amid a heated clash. Two titans of British geology, Adam Sedgwick and Roderick Murchison, had battled for decades over rock strata ownership. Sedgwick assigned them to his Cambrian framework. Murchison insisted on his Silurian. The feud turned ugly and vindictive, tarnishing Victorian scholarship. Lapworth scrutinized the fossils. He delved into graptolites, those peculiar colonial beings whose fossils crammed Welsh black shales, their fine etchings resembling inscriptions on rock. The term translates to written stone from Greek. He spotted what Sedgwick and Murchison, entangled in their rivalry, had missed. The fossils in those disputed layers stood apart, distinct from underlying Cambrian ones, separate from overlying Silurian forms. These strata held a unique assemblage, signaling a fresh phase in life's timeline. In 1879, Lapworth offered a solution. He defined a novel period, drawing its title from the Ordovices, an ancient Celtic group in northern Wales, and slotted it between the feuding classifications. The Ordovician arose from negotiation, from an educator's precise fossil analysis that the academics, distracted by squabbles, had failed to notice. The worldwide geological body didn't endorse the Ordovician formally until 1960, decades after Lapworth passed. Progress in science crawls. Solid concepts demand patience. Yet Lapworth proved correct. The Ordovician stood out as unique, a realm all its own, a segment of planetary history warranting its dedicated label. You're stepping into an epoch that defies ready comprehension in age. The Ordovician closed 443 million years back. Dinosaurs wouldn't emerge for 200 million more. They'd dominate 165 million years, then vanish for 66 million. Only afterward did human-like beings tread the ground. Measured against dinosaurs, the Ordovician isn't so remote. It predates the very idea of remoteness. Still, the strata hold the record. Fossils capture the inhabitants. Limestones shaping Egypt's pyramids originated on Ordovician seabeds. Layers of innumerable shells squeezed tight. Carbonate from creatures that sifted balmy, shallow waters, perished, sank, and solidified into rock. Marble gracing Greek shrines, stones erecting Gothic churches, paving slabs underfoot in historic European towns, all echo the Ordovician. The era spanned 42 million years. Within it, biology reshaped. Oceans teemed with unprecedented creatures. Land, though desolate, welcomed initial settlers. Weather swung from hothouse warmth to chillier tones, priming a disaster at the close. Waters stayed mild. Land masses submerged deep. Light penetrates all the way to the ocean bottom. In this expansive, sunlit shallows, life isn't sparse anymore. It's thriving. All-around creatures are sprouting, sifting for food, pursuing prey, seeking cover, and evolving. We've stepped into the Ordovician. After ages of constraint, the sea finally seems vast enough for expansion. It's balmy, brightly illuminated, and brimming with sustenance. As the environment evolves, so do the dynamics. The Cambrian sketch the initial designs, yet designs alone don't construct realities. Now, these inundated waters offered vacant niches waiting to be claimed, and organisms launched widespread trials in filtration, predation, concealment, and proliferation. This burst was so profound that it received an official designation: the Great Ordovician Biodiversification Event. Labels like that aren't coined for gradual shifts. They mark pivotal shifts evident in the fossil record, genuine plot twists in the narrative. For evidence, consider the numbers. At the Ordovician's outset, marine ecosystems supported roughly a few hundred genera of animals, around 450. By mid-period, that count had surged to about 1,400 genera, each representing a unique lineage in life's family tree, all coexisting in the expansive seas over submerged land masses. Seldom in Earth's timeline has marine variety climbed so steadily and vigorously. The Cambrian burst, millions of years prior, unveiled the primary body forms. The Ordovician made them thrive. If the Cambrian outlined the basics, the Ordovician added the intricacies, habitat by habitat, shore by shore, until the coastal waters buzzed with potential. The scientists who first identified this trend wrestled with how to label it. The Cambrian explosion had seized imaginations worldwide, its vivid title evoking visions of abrupt life's emergence from void. The Ordovician radiation, by contrast, was subtler, tougher to encapsulate or describe. It wasn't a blast. It unfolded gradually, enduringly, ubiquitously, reshaping marine realms across millions of years through a vast diversification. In 1995, a global initiative launched to catalog the phenomenon. Directed by Barry Webby, an Australian expert at Macquarie University, it united researchers worldwide, pooling insights on various fossil assemblages, eras, and locales. Compiling it all spanned almost 10 years. When Webby released the findings in 2004, he bestowed the official title, the Great Ordovician Biodiversification Event. The shorthand GOBE came naturally, as experts adore abbreviations, and it endured. The GOBE permeated educational materials, talks, and studies. At last, the Ordovician radiation gained a moniker to match the Cambrian explosion's flare. What sparked it? Scholars have pondered this for decades, yet the straightforward reply is uncertainty. The GOBE didn't stem from one trigger alone. It arose from an interplay of geologic, atmospheric, and biotic elements that forged an unparalleled opening. Paleogeography played a role. Continents dotted the planet, isolated by profound basins, yielding a wealth of varied environments. The warm platforms of Laurentia differed from those of Baltica, which varied from Gondwana's cooler edges. Every zone cultivated distinct wildlife, unique adaptations, tailored answers to existence and breeding challenges. When pathways occasionally linked via shifting flows, narrowing passages, or continental motion, thriving traits dispersed, blending with natives to spawn fresh hybrids. The breadth of shallow waters was key. Greater continental shelves equaled more territory, more spots for life to settle, more roles in the ecosystem to claim. The Ordovician's flooded lands supplied the Phanerozoic's, the past 540 million years, most extensive tropical shelf space. The terrain was primed, species rushed to fill it. The temperature drop might have been pivotal. The initial Ordovician's sweltering warmth moderated to chillier climes midway. Colder seas dissolve more oxygen. Higher oxygen enables bigger sizes, heightened vigor, and the energy needs of hunting, swift motion, and intricate actions. This moderation likely unlocked avenues the prior heat had blocked. Atmospheric and oceanic oxygen concentrations climbed. Though the exact path is contested, data points to a notable Ordovician uptick, possibly surpassing levels that enabled novel energy pathways, greater scales, and novel interspecies dynamics. Creatures requiring oxygen for respiration simply couldn't arise in seas lacking it. Yet as oxygen levels rose steadily in the Ordovician waters, that barrier dissolved, sparking chains of ecological responses that accelerated the early burst of species. Emerging hunters drove the evolution of novel protections among prey. Innovative suspension feeders tapped into food sources beyond the reach of seafloor inhabitants. Burrowing species reshaped the ocean bottom, generating tiny niches that invited colonization by other life forms. One breakthrough paved the way for the next. with the evolutionary surge building momentum through self-reinforcing loops. This wasn't just about swelling populations. It reshaped the very architecture of ocean habitats. During the Cambrian, the majority of marine life hugged the seabed, crawling over sediments, digging shallow burrows into the uppermost layers of muck, munching on microbial films, or picking at drifting detritus. The vast water layer overhead stayed mostly barren, an untapped vertical realm that few had mastered. The Ordovician upended that pattern. Life started reaching skyward. Crinoids, those sea lilies akin to echinoderms like starfish and urchins, fastened to the substrate with slender stems crowned by delicate fan-like appendages, sifting nutrients from passing currents. Certain specimens towered up to a meter tall, their fronds undulating in the flow to snag drifting plankton and organic scraps. In thick clusters, crinoids formed subaqueous forests, their stems bending like underwater reeds in an invisible breeze. Bryozoans made their debut. These communal builders crafting calcium-based exoskeletons in twig-like, sheet-forming, or intricate mesh patterns. Some stood erect, lending depth to the benthic landscape, while others coated rigid substrates, shells, stones, or even crinoid stems, fashioning multi-layered refuges for assorted creatures. Brachiopods, which had dotted Cambrian seas, exploded into myriad varieties, primarily suspension feeders. They pumped water across their hinged valves to harvest particles, then jettisoned refuse. In certain locales, they blanketed the bottom so thickly that the underlying ooze vanished from sight. Corals started erecting frameworks, too. Not the vibrant atolls of today's warm shallows, erected by scleractinians that wouldn't appear for another 200 million years. Ordovician reefs arose from tabulate and rugose corals, stromatoporoids, bryozoans, sponges, and assorted builders, familiar mainly to experts. Though modest in scale and less elaborate than contemporary versions, these were true reefs, multi-dimensional edifices protruding from the seafloor, offering havens, disrupting flows, and clustering biodiversity. The Cambrian bottom had been mostly even and straightforward, its assemblages arrayed in flat plains. By Ordovician times, the seafloor layered into tiers with life piled upon life, each stratum processing distinct water flows and harvesting unique provisions. This blueprint for ocean ecology would prevail through the ensuing 250 million years. In the words of paleontologist J. John Sapkowski, the Paleozoic evolutionary fauna took root in the Ordovician and matured in the epochs that followed. The surge wasn't even across the board. Various clades peaked at varying intervals, regions, and tempos. The opening stage, bridging the late Cambrian into the early Ordovician, spotlighted planktonic growth, the microscopic drifters anchoring marine trophic chains. Acritarchs, those enigmatic organic husks, possibly from algae, grew more varied. Chitinozoans, puzzling bottle-like microfossils perhaps laid as eggs by bigger beasts, emerged and proliferated. Graptolites, social floater danglers from buoyant frames, kicked off their proliferation. This plankton boom was pivotal since these floater form the foundational feast. Greater plankton variety supplied richer fare for consumers, from sieving filterers to stalkers of bigger drifters. The food chain's foundation broadened, propelling growth up through all levels. The central interval, spanning early to mid-Ordovician, focused on benthic gills. Brachiopods proliferated wildly. Bryozoans debuted and dispersed. Trilobites spawned fresh morphologies, foraging tactics, and evasion tricks against threats. Gastropods, snails and kin, multiplied, thriving as they rasped at biofilms and seaweeds on firm substrates. The closing stretch from mid to late Ordovician emphasized reef builders. Corals and stromatoporoids fashioned grander, more labyrinthine scaffolds, realms hosting hundreds of cohabiting species. The intricacy of ecosystems in Ordovician reefs came close to but never fully achieved the elaborate nature of today's coral systems. Across every stage, cephalopods kept evolving rapidly. They evolved into the top hunters of the Ordovician oceans, and their narrative warrants a separate exploration. The GOBE wasn't confined to specific locales. It unfolded across the globe, on all continents within every ocean basin. Local patterns differed, with various groups prevailing in distinct zones. Unique adaptations emerged in varied spots. Yet the broad path remained worldwide. Oceanic biodiversity expanded in Laurentia, in Baltica, in Gondwana, across the Iapetus Ocean and the Panthalassic Ocean, and in the intervening minor seas. This worldwide alignment has long intrigued scientists. Were the GOBE solely propelled by regional influences, like the traits of one shelf or another basin? We'd anticipate diversification, occurring at staggered times in response to contrasting circumstances. The approximate uniformity points to a deeper cause, perhaps a planetary-wide catalyst or facilitating factor impacting the whole Earth. The primary suspects are those we've already discussed. The paleogeographic setup, featuring expansive shelves and separated basins. The cooling climate that boosted oxygen levels. The ecological chains with their reinforcing cycles. It's possible that all played roles, or maybe undiscovered elements, lurk in the geologic layers awaiting future discoveries. The Ordovician has guarded its mysteries for roughly 500 million years. It still discloses them gradually, through individual fossils, individual chemical tests, individual meticulous investigations. In southern France's Montagne Noire area, hobbyist fossil hunters Eric Montser and Sylvie Montserrat-Goujon had pursued specimens since their 20s. They devoted countless weekend outings to trekking the slopes, examining exposures, and methodically cracking stones with steady chisel strikes. They understood their local geology as deeply as their backyard surroundings. During the early 2000s, they unearthed a remarkable find. The strata dated to the early Ordovician, around 470 million years old. The fossilization was outstanding. Not merely shells and rigid elements, but delicate tissues, guts, exoskeletons, features that typically vanish soon after an organism perishes. Over 400 specimens surfaced from one locality. Each offered a glimpse into a long-lost world near the South Pole, back when Gondwana sat at the planet's southern edge. Experts at the University of Lausanne examined the haul. Their findings, shared in Nature Ecology and Evolution in February 2024, unveiled a biota unprecedented for the early Ordovician. Arthropods, cyanidarians, sponges, algae. The variety was remarkable. The condition rivaled museum displays. The deposit earned the name Cabriere Biota, honoring the adjacent hamlet. This Cabriere Biota stands out because it proves the GOBE extended beyond warm zones. Even close to the poles in cooler waters far from the equatorial heat, organisms were branching out, innovating, occupying slots. The burst of life was genuinely universal, spanning steamy equatorials to frigid polar expanses. Eric and Sylvie Montserrat had devoted their existence to rock gazing. They cultivated the endurance essential to paleontology, the readiness to hunt for years yielding little of note, the resolve to press on regardless. Upon discovering the Cabriere's biota, they instantly grasped its significance. We shifted from wonder to thrill, Sylvie shared in a post-announcement chat. The research world followed suit, though more deliberately, pending scrutiny, evaluation, and verification that it was authentic. Montagne Noir's stones had concealed their tale for 470 million years. The Montserrat clan, armed with tools and tenacity, at last persuaded them to reveal it. Ordovician shallows burgeoned more swiftly than any prior or subsequent marine realm. The GOBE reshaped the principles of ocean biology, erecting layered habitats that would rule for the ensuing 250 million years. And amid those teeming depths, gliding past crinoid thickets, prowling over brachiopod meadows, one entity was scaling up, a tentacled form with a sharp mouth, destined to claim the role of the sea's inaugural supreme hunter. The relic measured bigger than a dinner plate, stretching 72 centimeters from front to rear. Its form captured in the subtle siltstone of modern-day Manitoba, Canada. The animal had perished 450 million years back on a warm, shallow seafloor, with silt enveloping it softly and thoroughly, locking in each joint of its segmented armor. In 1998, scientists carefully freed the fossil from its rocky tomb, only to discover it was the biggest intact trilobite specimen on record. They dubbed the species Isotellus rex, meaning the king, a fitting title indeed. Among the trilobites, Isotellus rex stood out as a colossal predator, patrolling the ancient seabeds of Ordovician Laurentia. With its wide, spade-like cephalon, it sifted through the muck in search of worms and other squishy creatures. Perched on tall stalks, its eyes kept watch for dangers or potential meals. The creature's robust, curved form, armored in thick calcite, prioritized strength over swiftness. Back in 1985, Ohio selected Isotellus as its official state fossil, honoring the era when these beings thrived in the warm, shallow waters blanketing the Midwest. Today, their traces linger in the Cincinnati area's limestone formations, embedded in the walls of historic homes, or exposed along interstate embankments. Spot the monarchs if you look closely enough. While Isotellus rex impressed with its scale, it wasn't unique in essence. The Ordovician marked trilobite's pinnacle era, an explosion of variety in species, habitats, and body designs. Over 22,000 kinds have surfaced from fossils, with the Ordovician hosting a hefty share. Trilobites had already spent 50 million years evolving before the Ordovician kicked off. They debuted in the early Cambrian, showing up varied and branched into clear family lines from the start. Their beginnings are still a puzzle. The oldest ones pop into the record fully developed, without clear precursors tying them to prior arthropods. Sometime in the late Ediacaran or dawn of the Cambrian, the classic trilobite blueprint took shape, and soon these critters blanketed the planet's seas. That design proved straightforward yet potent. 3 longitudinal lobes gave it the name, quote, 3+3, tagmata from head to tail, the cephalon up front, the thoracic midsection, and the pygidial rear. Crafted from calcite, the mineral behind limestone, their exoskeletons fossilized with exceptional clarity. Upon death, a trilobite's shell was practically primed to turn to stone. Cambrian trilobites did well but stayed constrained. many scraped by as detritus eaters, munching seafloor scraps. They tended to measure just centimeters and stuck to comparable forms, habits, and niches. The Ordovician upended that pattern. As global oceans reshaped their ecosystems, trilobites adapted in tandem, developing fresh ways to feed, sense, defend, and navigate both water and bottom. The old cautious Cambrian types yielded to a burst of innovation. Certain trilobites took to swimming. Ordovician waters teemed with ones that ditched the seabed altogether, morphing into free-floating pelagics akin to today's krill, drifting mid-water. These drifters boasted oversized eyes, sometimes encircling their domes for almost full-circle sight. Sleek and slim, with narrowed side lobes to cut resistance, they pursued tiny prey, or sieved bits from the flow, thriving in the open deeps away from the floor. Carolinites genesensis counted among these voyagers, its remains scattered worldwide. The U.S., Arctic zones, Siberia, Australia, China, sprawling across the Ordovician tropics. No seafloor dweller matched that reach. Carolinites hitched rides on ocean floes, chasing warmth and sustenance. The whole warm sea served as its domain. Such open-water trilobites likely mirrored krill in function, clustering in nutrient-rich zones to feed bigger hunters. They drove the Ordovician's watery overhaul, populating the vertical realms left vacant in Cambrian times. Meanwhile, other trilobites burrowed farther into the ooze than before. Those with cephala like plows delved into silt after infaunal worms, tapping layers beyond surface access. The mud turned into living space for concealment, pursuit, and sustenance out of sight from above. Predation ramped up too, forcing trilobites to evolve apace. Ordovician waters hid threats absent in the Cambrian. Cephalopods ballooning in size, speed, and appetite. Eurypterids, those sea scorpions, emerging with claws for grabbing and multifaceted eyes. Starfish had undergone significant evolution by this time. Their tube feet were adept at forcing apart bivalve shells, while their stomachs could extend to break down prey externally. For trilobites, each successive million years brought heightened perils to their existence. Their countermeasure came in the form of reinforced armor, sharp spines, and intricate embellishments that rendered them tough to ingest, agonizing to chomp, and costly to assault. Certain species developed spines of such extravagant length and complexity that they bordered on the comical, their forms adorned with protrusions designed to ward off any attacker, lacking a vulnerability to exploit. Selinopeltis, hailing from the Ordovician strata of Europe and North Africa, bore spines that stretched well beyond its frame in various orientations, transforming the creature into something resembling a knight's armament more than a natural organism. Additional trilobites gained the capacity to curl up, coiling their bodies into compact spheres that shielded their vulnerable undersides under the sturdy vault of their exoskeletons. This enrollment strategy wasn't entirely novel. Some Cambrian trilobites possessed it too, but the Ordovician era refined it to a fine art with the emergence of fitted joints that enabled a seamless seal, offering predators nothing but a polished calcite orb. Flexicali main, prevalent in the Ordovician formations of Ohio and nearby regions, exemplified this skill superbly. Its remains frequently appear fossilized in the coiled state, locked in the very guarded pose that protected it during life, be it from a sudden peril followed by swift burial, or merely expiring in its habitual defensive curl. The fossils offer no clues on that front. Yet they do demonstrate that this adaptation proved effective, enduring through countless preserved examples over vast timescales. Trilobite vision stood out as one of the planet's most advanced optical apparatuses up to that point. These were compound eyes akin to those in today's insects and crustaceans, formed from numerous tiny lenses arranged in a domed configuration. In contrast to the pliable organic lenses of insects, however, trilobite eyes utilized calcite, pure crystalline calcium carbonate, identical to their shell material. These were literally stone-built eyes, with lenses durable enough to endure fossilization and retain the intricate optics of beasts long extinct by hundreds of millions of years. Calcite's nature introduced a challenge. Its birefringence fractured light into dual beams, yielding fuzzy, doubled sights that would hinder any creature scanning for threats or hunting quarry. Trilobites addressed this with a sophistication lost to human ingenuity until the 1600s, by aligning the lens's crystalline orientations to curb birefringence and in select species adding a compensatory chitin overlay to offset lingering aberrations. They crafted achromatic doublets, precise imaging systems predating the insights of Christian Huygens and René Descartes by eons. Certain Ordovician trilobites featured eyes perched on elongated stalks, elevated like surveillance towers over their torsos. Asaphus Kali, from Russia's Ordovician deposits, sported stalks so lofty that the animal could submerge its bulk in the mud while keeping watch overhead, alert to dangers, opportunities for sustenance, ever vigilant with boundless endurance. In contrast, some lineages forfeited eyesight altogether. Within abyssal depths, subterranean caverns, or lightless realms, vision offered no advantage, merely a drain on resources without benefit. Eyeless trilobites arose multiple times, their ocular regions flattened and unadorned, likely bolstered by heightened alternative perceptions to navigate the gloom. Ordovician trilobites weren't just plentiful and varied, they permeated every corner. Step into any museum boasting an Ordovician fossil exhibit, and trilobites command the spotlight. Browse a paleontology vendor, and Ordovician specimens crowd the inventory. Elrathia from Utah, Phacops from Morocco, Calamine from Britain, Isotolus from Ohio. These icons encapsulate Paleozoic fame, embodying the age in collective memory. Their prevalence among collectors mirrors their dominance in ancient ecosystems. Trilobites ranked among the Ordovician Ocean's most ubiquitous inhabitants, thriving across nearly all aquatic habitats and spanning functions from carrion eater to hunter, filterer of plankton to bottom dweller. A standard Ordovician ocean bottom teemed with several trilobite varieties. Each carved out its own ecological slot, sidestepping rivalry via nuanced shifts in feeding habits, activities, and localized surroundings. The sheer variety could overwhelm. Certain sites have unearthed scores of coexisting trilobite kinds, all sharing one seafloor expanse, yet dividing sustenance so meticulously that harmony prevailed. The ways in which these creatures managed to live together are still somewhat enigmatic. Evidence shows us that such harmony existed, yet piecing together the environmental specifics from remains dating back nearly 500 million years demands deduction, creative insight, and precise examination of mouthparts, fossil tracks, and surrounding rock layers. What stands clear is that Ordovician trilobites had mastered the challenge of sharing space. They had adapted to a world growing ever more packed. This density wouldn't endure. As the Ordovician drew to a close, disaster arrived. The great die-off that ended the era, ranked as the second most devastating in Earth's timeline, striking trilobites with particular force. Whole lineages were erased. Entire roles in the ecosystem vanished. The active swimmers, the burrowers, the spine bears, the stalked hunters all suffered massive losses, their variety plummeting, their reign concluding. Trilobites endured beyond the extinction. They persisted for 200 million more years, only to fade at the close of the Permian. Still, they never regained their Ordovician splendor. The trilobites, after that event, formed a reduced assembly, far less varied, far less commanding in their niches, gradually pushed aside as other arthropods, like crustaceans and chisarites, gained ground. The Ordovician marked their zenith, the era when trilobites commanded the ocean floor, when their protected forms blanketed the shallow bottoms across all lands, when their faceted eyes surveyed waters from the poles to the tropics. By the period's start, they had been evolving for 50 million years. Another 250 million lay before them. But the order of vision represented the pinnacle, the peak from which the rest was an extended, gradual decline. Trilobites held sway over the seabed. They divided that domain with brachiopods and bryozoans, with crinoids and corals, with worms and snails and obscure soft-bodied forms that failed to fossilize. They vied for sustenance, territory, and endurance, and at times they gazed upward through their crystalline eyes toward the depths overhead. Motion stirred in those layers. Something massive, something with trailing tentacles, a spear-shaped shell, and a beak capable of shattering calcite plating as simply as one might split an egg. Trilobites weren't the sole rulers of the Ordovician oceans. A 6-meter shell, tapered to a point like a lance. Within dwelled a cephalopod, kin to today's squid and octopus, though it bore no resemblance to those flexible heirs. Its form filled just the widest section, at the broad base of that vast taper. Trailing behind were chamber after chamber of hollow shell, separated by arched partitions known as septa. A slender tissue conduit, the siphuncle, linked each to the creature's body. Via this passageway, the cephalopod could tweak the gas levels in its compartments, controlling its flotation and gliding up or down the water layers with little exertion. The genus was Endoxeris. Its remains appear worldwide, in North America, Europe, China, Australia, the fragmented legacy of a hunter that once ruled the Ordovician waters. The biggest verified fossil spans 3 meters in its current state, though the tip is fractured and absent. Estimates indicate the complete form neared 6 meters long. Dubious accounts hinted even grander ones, close to 9 meters, but such assertions are debated. Endoxeris stood as the planet's most colossal creature to date, surpassing any Cambrian life form and outscaling the huge anomalids that prowled prior oceans. Life's Chronicle now featured a genuinely gigantic swimmer for the first time, a beast that devoured whatever crossed its path, against which even trilobites' tough shells offered scant protection. The era of immense cephalopods had dawned. Cephalopods arose in the late Cambrian, stemming from a sluggish, snail-resembling forebear that figured out how to build a partitioned shell. The breakthrough lay in managing buoyancy. A typical snail hauls its shell as inert cargo, hauling it over the bottom at sluggish paces, confined to seafloor life. Early cephalopods realized that by closing off shell segments and inflating them with gases, they could levitate. The shell turned from a drag into a lift mechanism. The organism could ascend into open water, propel itself, and tap into food sources unreachable by bottom dwellers. Cambrian cephalopods stayed modest in size, their shells gauged in centime. They were probing a fresh lifestyle, exploring the potentials of flotation and propulsion. Not yet widespread, not yet plentiful, the order of vision altered it all. As the globe reshaped sea habitats, cephalopods diversified in parallel with the surge. Fresh shell designs emerged. Linear cones, bent cones, spiraled forms that later inspired the ammonites of future times. With rising oxygen concentrations and greater food availability, cephalopods could attain unprecedented dimensions. The stratified habitats fostered by the Ordovician period unlocked fresh predatory niches for creatures adept at navigating up and down the water strata. Nautiloids, encompassing this broad array of primitive cephalopods, proliferated into countless varieties. Certain ones stayed compact, occupying slots as intermediate hunters or detritus feeders. Many others expanded dramatically in scale. Straight-shelled orthocones, such as Endoceras and its kin, emerged as the dominant hunters of their epoch. Hunting posed unique challenges for a creature measuring 6 meters in length with a streamlined, torpedo-like form. Debates persist over the locomotion of orthocones. They weren't swift swimmers. Their linear shells generated significant resistance, and their orientation remained upright in the aquatic environment. Their jet-based propulsion likely paled in efficiency beside that of today's squid. Experts largely agree these were stealthy ambushes, either drifting close to the ocean floor or suspending themselves mid-water until quarry ventured nearby. The strike would strike without warning. Cephalopods boast tentacles, robust limbs equipped with suckers or barbs that seize victims and pull them to the mouth. Nestled amid these appendages is a sharp beak, a chitinous, parrot-resembling tool designed to shear through shells, plating, or any resistance from ensnared quarry. Endoceras might have ensnared a trilobite with its tentacles, shattered the calcareous carapace using its beak, and devoured the vulnerable innards. Fossil proof supports this scenario. A late Ordovician trilobite from Ontario, identified as pseudogygites, displays a puncture wound aligning precisely with a cephalopod beak's profile. The trilobite perished from the assault, unable to shed its shell, recover from the injury, or evade burial with the fatal proof etched eternally in rock. The lesion's dimensions correspond to beaks from Camarasaurus, a near relative of Endoceras, unearthed in the identical deposits. This stands as paleontology's analog to a forensic snapshot. The hunter, the victim, the lethal blow, all etched indelibly over 450 million years, awaiting deciphering by keen observers. Cephalopods didn't dominate unchallenged. They coexisted at the top tier with another faction, even more bizarre in form. Eurypterids, those ancient sea scorpions, surfaced in Ordovician strata, their frames encased in armor, forward limbs adapted into seizing pincers or rending spikes. As arthropods linked to today's horseshoe crabs and spiders, some attained impressive girth, not rivaling the colossal orthocones, yet substantial enough to menace seafloor denizens, sufficiently robust to vie for meals to hold sway. Megalograptus ranked among the Ordovician Eurypterids, a hunter, roughly a meter in extent, its leading appendages fitted with spines to snag prey. It likely stalked across or along the bottom, targeting trilobites, annelids, lesser arthropods, whatever it could overpower. Subsequent eurypterids ballooned further, hitting 2 meters or beyond in Silurian and Devonian times, though even Ordovician versions commanded respect. Sandwiched between overhead cephalopods and undersea eurypterids, Ordovician oceans turned perilous. The Cambrian era featured diminutive threats from anomalocarids and priapulid worms, dangers spanning mere dozens of centimeters. The Ordovician amplified the peril. Predators spanning meters now prowled the depths. Trilobite defenses, plating, protrusions, coiling, and tunneling arose as countermeasures to this escalated menace. The evolutionary contest ignited, that perennial interplay of pursuer and pursued, propelling life's trajectory for 500 million years hence. The Ordovician set the blueprint. All that followed merely riffed on its motif. Enormous cephalopods spanned multiple branches. Endocheras and endocerid featured telltale inner architecture, conical deposits inside its siphuncle, possibly acting as ballast to steady the shell for level orientation. Camaroteras shared this lineage, matching in stature and habitat. Alternative nautiloid clans devised distinct adaptations. Actinocerids crafted intricate internal frameworks, potentially enabling quicker shifts in buoyancy. Tarphicerids spiraled their shells, yielding tighter, more agile designs. Elasmorocerids drastically condensed theirs, forging blunt, projectile-like bodies that might have outpaced their slender counterparts in speed. Such morphological variety mirrored the array of habitats. Ordovician waters teemed with specialists tuned to varied depths, targets, and tactics. Some roamed the pelagic zones, others skulked by the substrate. A few could have been proactive chasers, pursuing quarry vertically through the currents. Certain ambush predators among them undoubtedly saved their strength, waiting motionlessly until suitable prey ventured close enough to strike. We lack direct views of their pursuits, unable to witness their habits, group dynamics, or mating behaviors. All that's left are the exquisite yet puzzling shells, plus scattered signs of attacks, like a scar from a bite or a fractured casing, that suggest the brutal realities they endured. The endocarids hit their zenith during the mid-Ordovician and then began to wane. This trajectory is a familiar one in the study of ancient life. A clade arises, branches out, rules briefly, and eventually recedes, supplanted by fresher branches, more attuned to shifting environments. Endocarids yielded to rival nautiloid clades, with their enormous straight shells growing scarcer in the later Ordovician deposits. Toward the period's close, as the great die-off loomed, the colossal forms had already become scarce. They perished in that event. The mighty straight-shelled behemoths, those 6-meter terrors dominating the Ordovician seas, all disappeared amid the era-ending disaster. A few nautiloids endured, carrying on into the Quran, and further, ultimately leading to the lone, extant genus, Nautilus, which still glides through Pacific depths. Yet the Titans were lost forever. Their dominant phase spanned roughly 50 million years. During that span, they reshaped ocean dynamics, imposing selective forces that spurred protective adaptations across all targeted species, setting the template for top-tier hunting that would define sea life indefinitely. From sharks and mosasaurs to plesiosaurs and orcas, every subsequent ocean stalker traced its lineage back to the blueprint laid by endocheras and relatives. These massive cephalopods, pioneered the archetype of the sea's supreme hunter. Later arrivals built upon their legacy, consciously or not. Away from the profound hunting zones of the vast orthocones in the balmy coastal areas, cephalopod evolution pressed on with diminutive variants. Coiled nautiloids were emerging, their housings twisting into efficient spirals that traded elongation for agility. These forebears of the ammonites, the lineage set to rule Mesozoic waters with an array of spiral designs, were taking shape. Ammonites wouldn't emerge for 100 million more years, but in the Ordovician their architecture was being prototyped, honed and primed for eventual triumph. Modest orthocones hung on too, occupying roles as intermediate hunters, detritus feeders, or possibly even plankton strainers. The cephalopod form proved remarkably flexible, open to tweaks for virtually any oceanic niche. What started as a buoyant mollusk evolved into an imperial line, spawning everything from colossal squid and chambered nautiluses to octopuses, later hailed as Earth's cleverest soft-bodied creatures. Ordovician cephalopods were trailblazers. They probed potentials that offspring would expand across 500 million years. They scaled up predation, showcasing the prowess of a swift, brainy, arm-bearing pursuer in prey-rich waters. Today's tentacled colossi are extinct, their casings squashed into rock layers, fleshy parts rotted irretrievably. We're left with deductions, models, and the meticulous efforts of fossil experts, analyzing shell shapes, increment patterns, and chemical signatures to unravel their existence. The resulting image is patchy yet intriguing, a rough outline, not a full rendering. Once, these behemoths cruised these waters, their silhouettes darkened bottoms teeming with trilobites foraging, brachiopods sifting, and crinoids undulating in bygone flows. A 6-meter conical armor, arrow-like, sliced through temperate Ordovician seas. Trilobites and cephalopods animated the waters with pursuit and evasion, enacting the timeless saga of hunter and hunted. Deeper down, fixed to the substrate, another life tier thrived. Creatures that neither stalked nor slew, but sieved and constructed, the steady framers of a layered realm. They had remade the seabed into a landscape alien to Cambrian eyes. They erected vertically. Cambrian existence clung low, skimming sediments, tunneling through silt, nibbling microbial films blanketing substrates. The overlying volume stayed mostly vacant, a vast expanse few had mastered. Edible bits floated by unclaimed. Flows dispersed riches unharvested. The sea resembled a dwelling used only at basement level. Ordovicians erected levels atop it. Layers mounted over layers. Existence layered onto existence. The simple, two-dimensional habitats of the Cambrian evolved into layered ecosystems, with creatures inhabiting separate strata. Each layer processed unique water flows and tapped into specialized resources. On the seafloor bottom, brachiopods formed a thick mat. These shelled creatures, which resembled bivalves like clams but belonged to a distinct lineage, had appeared back in the Cambrian era. Yet, the Ordovician marked their explosive diversification. Hundreds of genera sprang up, tailored to every imaginable type of seabed, depth, and water condition. Certain species secured themselves to stones via soft pedicles. Others rested loosely on the mud, relying on their mass to stay put. Some more adhered firmly to solid substrates, fixed in place forever, as they drew in currents through their valves and sifted out particles using fine lopophores. In various Ordovician formations, this brachiopod layer proved incredibly thick. Their casings crowd together so densely that no underlying sediment shows through. Though each was tiny, spanning just a handful of centimeters, they collectively created a vibrant mosaic, a living base for other life to settle upon. Rising over the brachiopods came the bryozoans. These were relative newcomers. The earliest clear bryozoan fossils date to the early Ordovician, positioning them as one of the final major animal groups to show up in the fossil archives. As colonies, they consisted of minuscule zooids, each under a millimeter long, though entire assemblages could stretch across meters. The zooids produced calcite exoskeletons, forming twig-like coating or intricate lattice shapes that projected upward from the bottom like tiny forests. Every zooid used a crown of tentacles to strain the water, snagging microbes and detritus, then sharing the bounty via interconnected body walls. This group-living approach proved highly effective. An isolated zooid stood helpless, tiny and unable to alter its surroundings. But a throng of thousands turned into a habitat builder, generating vertical complexity from nothing, offering shelter to myriad species, and reshaping how water moved over the seabed. Bryozoan growths displayed shapes that bordered on the engineered. Some appeared fragile and net-like, as slim calcite panels riddled with countless pores, each a dwelling for a zooid. Others grew sturdy and forked, with walls robust enough to withstand currents and endure for years or even decades. Additional types coated rigid surfaces, shells, boulders, crinoid stalks, spreading like a vital glaze over whatever they could cling to. The assortment was immense. Today's bryozoans encompass around 6,000 species, and the Ordovician burst laid down their core variety, testing colony designs that would endure for the next 500 million years. Even taller loomed the crinoids. As echinoderms, crinoids share kinship with starfish and sea urchins, yet they bear little resemblance to those mobile relatives. A standard crinoid features a stalk, a pliant stack of calcite plates, rooted to the bottom at its base and topped by a cup-like theca, encircled by slender arms. These appendages bear tube feet that snag drifting bits from the flow, channeling them along channels to the core mouth. The overall look evokes a blossom. 19th century scientists dubbed them sea lilies, a label that endures. In truth, crinoids are animals, not flora, and their elegant limbs serve for foraging, not show. A field of crinoids undulates in the tides like blooms bending in a breeze, everyone fluttering its rays to rake in sustenance. Ordovician crinoids attained impressive stature. Certain kinds soared to a meter or beyond, their columns hoisting the feeding calyxes into clearer waters beyond the grasp of the brachiopods and bryozoans underneath. They acted as tiered foragers in the upper reaches of the seafloor assemblage, sifting flows untouched by the lower dwellers. The stalks posed their chief weakness. Rooted fast, a crinoid couldn't escape threats or shift spots amid shifts in the environment. Should a cephalopod or eurypterid strike, it might only pull in its arms and trust its calcite armor for defense. Plenty failed to make it through. Broken crinoid stalks strew Ordovician seabeds, shattered husks of beasts uprooted, their thecas and rays fractured and scattered. Still, they thrived. The method succeeded sufficiently to define many Paleozoic ocean scenes. Crinoid remnants rank among the most plentiful in Ordovician limestones, with their plate-like ossicles piling up so profusely that entire strata consist mostly of their cast-offs. This tiering extended beyond the structural. It fostered a split in niches, enabling far more species to thrive together than any flat-bottom setup could sustain. Imagine a section of Ordovician ocean bottom. Brachiopods sift through the water, right at the sediment level, snagging tiny particles that have floated down from higher up. Bryozoans positioned a bit above at a few centimeters strain water beyond the brachiopod's grasp. Crinoids, towering even taller, tap into flows that skim past the bryozoan clusters without disturbance. Every level taps into its own layer of the water column, claiming a unique share of the drifting nutrients. This setup represents niche partitioning, the biological strategy that lets rival species share space without clashing. Had these creatures all targeted the same currents, fierce rivalry would erupt, with the top performer driving out the rest. Instead, slicing the water vertically into layers cuts down on overlap, fostering higher variety than a flat, single-level setup could handle. It was during the Ordovician that this framework emerged. The stacked communities of suspension feeders that would rule ocean habitats for the following 250 million years, spanning the Silurian, Devonian, Carboniferous, and Permian. The blueprint took shape back then. All that followed was just refinement. Paleontologist Jack Sepkoski, who devoted his work to tracing biodiversity trends in fossils, labeled this the Paleozoic evolutionary fauna. It stood apart from the prior Cambrian assemblage, centered on trilobite-led sediment-munching groups. It also differed from the eventual modern lineup, marked by bivalve and gastropod booms. That Paleozoic crew became the Ordovician's legacy to future eras, a model for structuring sea life systems. From those layered seabeds, reefs began to emerge, but the term demands precise explanation. Today's coral reefs rely mainly on scleractinian corals, which didn't appear until the Triassic, some 200 million years post-Ordovician. Back then, reefs operated differently, assembled by varied builders employing unique construction methods to yield distinct sizes and intricacies. The architects were diverse. Tabulate corals supplied their clustered skeletons, each one a small tube, with thousands fused into dome-like or branching forms. Rugose corals brought single or group-based shapes, their inner designs set apart from the tabulates. Stromatoporoids, mysterious creatures whose exact relations still spark debate, erected hefty calcareous frames that could anchor entire reef cores. Bryozoans lent their delicate, net-like builds. Sponges contributed their siliceous or calcareous forms. Together, this mix formed a partnership, with various players both aiding and vying to erect towering edifices that protruded from the flat sea floor. These Ordovician reefs fell short of modern coral giants in scale. They never created sprawling barriers running thousands of kilometers along tropical shores today. Ordovician versions were mostly patch reefs, standalone hills jutting from the bottom, seldom exceeding a few meters in height or a few hundred meters wide. Still, their impact on ecosystems was profound. A reef generates living space. Its rugged vertical profile offers refuge to fish, crustaceans, mollusks, and myriad creatures unable to build their own hideouts. Its faces provide attachment points for clinging species, drillers, or any needing a firm base amid the mushy ooze. Those Ordovician reefs stood as pockets of intricacy amid otherwise even seas. magnets for species buildup. Beyond reshaping the water above, the suspension feeders altered the ground below. A brachiopod pulls in water, pulls out edibles, and spits out refuse. That refuse drops to the bottom, organic bits bundled into pellets that nourish sediment grazers underneath. Crinoids perform similarly from their elevated spots, showering waste onto the layers below. These feeders weren't solely sustaining themselves. They nourished the base, turning airborne morsels into seafloor bounty. Known as biodeposition, this shift redefined ocean sediments. Cambrian floors gathered organics gradually, relying on whatever physics sent sinking from the depths. Ordovician bottoms got a boosted downpour of processed organics from the sieves overhead. The seafloor grew more fertile, backing a surge in sediment eaters, diggers, and detritus-dependent life. The cycles fed on each other. Greater numbers of suspension feeders spurred more deposition. That buildup supplied richer fare for bottom dwellers. In turn, expanding deposit feeders ramped up bioturbation, the stirring and reworking of mud by burrowers, that freed up nutrients to fuel more plankton growth, ultimately provisioning even more suspension feeders. The Ordovician ecosystem operated like a self-reinforcing engine, boosting its overall productivity. Every element bolstered the rest. Traces of this layered realm appear in museum displays worldwide. Limestone blocks teem with preserved organisms. Brachiopod shells packed together into thick carpets. Bryozoan colonies extend and fan out over the stone. Crinoid stalks litter the surface like toppled pillars, their calyx-shaped tops sometimes intact, with arms outstretched in death, just as they extended in life. Tabulate coral groups create shadowy clusters, their minuscule coral lights revealing honeycomb designs on eroded faces. These stone-frozen moments capture entire communities, safeguarded by the gentle sediment buildup that enabled such variety to thrive. The creatures perished, got buried, compacted, and turned to rock. And today they rest in display cabinets tagged with scientific Latin labels, ready for a viewer to gaze and imagine the vibrant society they once formed. Such imagination demands work. A fossil block isn't a full habitat. It's a tangle of shells, a mess of broken bits, a riddle short on clues. Soft-bodied life vanishes without a sign. Original positions warp from crushing and erosion. Time gets flattened out. Beings separated by years or ages end up squeezed into one bed, their chronological gaps hidden. Experts in paleontology devote lifetimes to deciphering these blocks, pulling ecological insights from the disorder of decay. They assess shell alignments to deduce water flows. They examine growth patterns to grasp group behaviors. They investigate the drillers and settlers that overtook shells post-mortem, piecing together the aftermath timeline for the assemblage. Every block reads like a passage in a forgotten tongue, and mastery builds gradually. This stratified setup etched its mark in the rock. Brachiopods at the base, bryozoans higher up, crinoids stretching for the top. The entire setup shaped by rivalry and symbiosis, plus the dynamics of ocean currents. Filter feeders among the orders had reshaped how seafloor societies assembled. Predators and prey navigated their groves, their fields, their enduring frameworks. Deep under this bustling framework, hugging the bottom, another presence was emerging. An utterly distinct form of life, evolving in the shadowed depths of Ordovician oceans from the era's start. The earliest vertebrates, armor emerged before jaws, 500 million years back in the Cambrian's coastal waters. a revolutionary find, entered the fossil archives. A modest, soft-bodied animal with a rigid rod along its torso. A notochord, the hallmark of our phylum. Pikaia, from the Burgess Shale, wasn't a true fish. Lacking bones, scales, or proper fins, it resembled a twisting strip of flesh, maybe 5 centimeters in length, propelling itself via body waves in seas that later rose into the Canadian Rockies. Pikaia marked the origin. Vertebrate evolution stemmed from forebears like it, from delicate chordates that barely fossilized, beings so perishable they needed rare conditions for traces to endure. Cambrian chordates stayed scarce, tiny minor figures amid arthropod rule. The Ordovician shifted their fate. In the era's opening phases, a chordate branch developed a fresh adaptation. It started mineralizing its body, crafting rigid elements from calcium phosphate. The stuff that later built your dentition, your framework, the bones supporting your stance. Initial vertebrate hard tissues weren't inner frames. They were outer plating, bony shields over the skull, and anterior defenses in a growingly hazardous environment. Thus dawned the armored fishes. Experts dubbed them ostracoderms, shell-skinned, though it's a loose label, lumping various lines that separately devised parallel fixes for shared challenges. All lacked jaws, their feeding ports basic slits ideal for straining food or drawing organics from muck. They stayed diminutive, sized in centimeters over meters. They moved ponderously, their weighty coverings curbing agility and pace. Yet they birthed every backboned being to come. Arandaspes and Pionotops glided in the warm shallows blanketing Central Australia 480 million years ago. Their remains hail from the Stairway Sandstone in the Northern Territory, deposits from a seafloor setting when Australia sat within Gondwana, near the equator, with shores lapped by balmy Ordovician waves. Arandaspes was first found in 1959 and received its official scientific description in 1977. It ranks among the most ancient ostracoderms documented, with fairly intact remains. This creature likely measured about 15 centimeters in length. Its head featured a robust bony covering. That shield was decorated with raised ridges and small knobs. The eyes sat laterally, offering a broad visual range. After the head plate, the trunk was shielded by numerous tiny scales, each one a miniature bone segment. This setup delivered solid defense, yet permitted enough movement for effective swimming. The tail likely served as the primary driver for locomotion, whipping from side to side, much like in today's fish. Arandaspes lacked jaws entirely. Instead, its mouth formed a basic opening at the head's front, likely edged with flexible tissue to draw in water and sift out tiny organic bits. It wasn't built for hunting, unable to chomp, rip, or chase down victims with any ferocity. Rather, it was a gentle forager, a sieve-like feeder thriving on minuscule and sluggish morsels. Such a lifestyle might appear modest, yet it marked a breakthrough. Arandaspes and its kin represented the initial vertebrates to etch a substantial trace in the fossil archives, the earliest in our evolutionary branch with forms sturdy enough to endure through eons of Earth's history. They were trailblazers, testing out a blueprint that would later spawn sharks and salmon, frogs and falcons, dinosaurs and dolphins, plus one odd branch of African apes destined to ponder their roots. That bony plating evolved as a counter to hunters. The Ordovician oceans teemed with peril. Cephalopods prowled the depths using tentacles and sharp beaks. Eurypterids prowled the bottom with pincer-like limbs. Enormous carnivorous arthropods, perhaps holdovers like anomalocarids from the Cambrian or their Ordovician offshoots, added further dangers. A vulnerable, soft-bodied chordate, drifting lazily in those currents, would make an effortless target. A shift was essential. The advent of bone transformed the game. It created a tough barrier between hunter and hunted, a barrier that beaks struggled to pierce, plating that claws could rake across without gaining traction. But the price was steep. Bone adds weight and demands heavy metabolic investment to build and sustain, a load that hampers quickness and nimbleness. The payoff? Endurance. These plated swimmers survived to pass on their genes. The unprotected ones didn't. This dynamic echoes throughout subsequent evolution. Turtles developed their shells. Armadillos grew bands of bone. Pangolins formed keratinous scales. As hunting pressures mount, defensive plating often emerges as a strategy, sacrificing some swiftness for safety that proves effective under suitable conditions. The ostracoderms discovered those ideal niches. They proliferated across the Ordovician, colonizing the near-shore waters of various landmasses. Sacambaspes from Bolivia indicates they ventured to Gondwana's edges. Astraspis out of North America confirms their foothold on Laurentia. By the later Ordovician, these jawless, armored swimmers formed a small yet solid part of global marine communities. Their fossils remain scarce, but their significance endures. The study of vertebrate fossils grapples with biases in what gets preserved. Bones endure fossilization effectively, but solely under rapid burial in optimal settings. Only when the surrounding sediments support it, and later, earth processes spare the remains. Soft tissues seldom make it. Cartilage preserves badly. Bone itself can vanish if acidic waters seep through. It might shatter under intense burial forces or wear down via exposure before discovery. Thus, the Ordovician vertebrate traces are spotty at best. Scattered scales, incomplete head plates, rare, fully connected finds from special sites. Scientists piece together these beasts from shards, deduce forms from scraps, and assemble the story of primitive vertebrate development from clues that could scarcely stock a single exhibit shelf. What those clues reveal is an explosive spread. Various lines of jawless fish arose separately, crafting diverse armor layouts, body forms, and ways of life. Heterostracans sported massive head shields enveloping the body's forward section. Anaspids displayed slimmer, bendier plate setups. Thelodonts were blanketed in fine scales, yielding sleeker profiles and possibly livelier habits. None of these clades persist today. Each, though, enriches our grasp of vertebrate origins, how the core design was tweaked and honed, how the path leading to toothed fish and ultimately humanity arose from toothless forebears. A jaw-free mouth feels restrictive. In truth, it was the starting point. Your own jaws trace back to gill arches. Those skeletal frames propping fish gills gradually reshaped over countless generations into biting mechanisms. The initial gill arch developed into the actual jaw structure. The subsequent one formed the hyoid system, which underpins the tongue. This shift took place following the Ordovician during the Silurian or Devonian periods, giving rise to gnathostoms, the jawed vertebrates that eventually came to rule both marine and land habitats. Ostracoderms lacked jaws entirely. They embodied the original vertebrate form, the blueprint of anatomy prior to that pivotal change. Delving into their fossils means uncovering our remote origins, tracing the foundational design from which our own anatomy sprang. Being jawless doesn't imply any inherent inferiority. Modern survivors like lampreys and hagfish stand as highly adapted species, thriving in specific ecological roles and achieving abilities beyond the reach of their jawed counterparts. A lamprey, for instance, can latch onto a host using its suction-like mouth, scrape away scales and flesh, and sustain itself on blood and tissues for extended periods. Hagfish, meanwhile, can contort their bodies into loops for better grip, release vast amounts of mucus to ward off threats, and endure long stretches without nourishment. Far from evolutionary dead ends, these represent viable alternatives, divergent routes that most vertebrates forsook, yet ones that proved effective in their domains. During the Ordovician, ostracoderms tested various evolutionary avenues. Certain traits faded away, while others evolved into novel features. The vertebrate form proved flexible, adaptable, and attuned to selective forces that we can only dimly infer from preserved remains. Venturing onto land lay eons ahead. The earliest vertebrate tracks on dry ground wouldn't emerge until some 60 million years later, in the late Devonian. True land dwellers, amphibians able to complete their life cycles ashore, required even more time. In the meantime, Ordovician ostracoderms remained wholly ocean-bound. Their forms were optimized for navigation through water. Their biology relied on aquatic surroundings for breathing, breeding, and all facets of survival. Nevertheless, untapped potential lurked within. The vertebrate template harbored options that even the most visionary of those ancient fish couldn't foresee. Lungs would later arise from swim bladders. Limbs would sprout from fin structures. The plated defenses shielding Arandaspis from Ordovician hunters would relocate inward, reshaping into the internal skeleton that bolsters your frame today. Evolution operates without foresight. It lacks vision of tomorrow, unable to predict which traits might serve in uncharted realms. Ostracoderms developed plating because it offered clear advantages in their Ordovician world. They had no inkling that their heirs would tread soil, soar skies, or one day craft devices to escape the world altogether. At its core, the vertebrate saga unfolds as one of metamorphosis. Every lineage tunes itself to immediate realities, oblivious that it also bridges the past and the unfolding future. Ostracoderms served as our forebears, gliding through balmy Ordovician waters, shielded from visible perils and bearing the latent sparks of destinies beyond imagination. Early backbones consisted of basic notochords reinforced by cartilage, with mineral reinforcements focused on outer plating rather than bony cores. Subsequent eras brought greater intricacy to this framework. The spine, divided into segmented vertebrae, ribs safeguarded vital organs, and skeletal elements in limbs enabled diverse movement styles. Ordovician vertebrates resembled initial prototypes, preliminary outlines that future developments would refine and expand. They navigated amid crinoid thickets, across brachiopod fields, under the looming forms of colossal cephalopods. They sifted nutrients from currents already strained through bryozoans and corals. In that vast web, they played minor roles, dwarfed by trilobites, nautiloids, and the dazzling array of soft-bodied creatures. But their modest status wouldn't endure. Their descendants would eclipse trilobites, outlive those immense cephalopods, and surpass nearly all the Ordovician Ocean's heavyweights. Vertebrates bided their time. They could afford to. As plated swimmers scoured seafloor muck for sustenance, as sieving communities stacked their layered realms, as hunters pursued and quarry evaded, another shift stirred elsewhere. Remote from teeming bottoms, away from cephalopod grasp and eurypterid pincers, existence ventured into the bold unknown. Pioneering life forms began inching toward shore. Not all life pulsed with motion. Some merely suspended in the currents. Ordovician seas brimmed with plankton. Tiny drifters, too frail or minuscule to resist the tides, borne passively by the flow. Among them were single-celled forms unseen without aid, anchoring the trophic chains that nourished the entire hierarchy above. Certain drifters grew bigger and formed colonies, with structures optimized for buoyancy over active movement. They passed their existence, buoyed along by the flows of an immense global ocean. Among these floaters, graptolites stand out for their remarkably clear fossil traces. These were communal creatures where each group comprised scores or even hundreds of minuscule zooids, each nestled in cup-like cups aligned along single or multiple stems. Those stems consisted of collagen, a protein that typically breaks down swiftly post-mortem. Remarkably, though, graptolites fossilized with elegance, their intricate forms captured as thin carbon layers on dark shales, subtle black streaks resembling faint etchings from a pencil on stone. Their name echoes this look. Graptolite comes from the Greek words graptos, or written, and lithos, or stone. Naturalists in the 1800s, upon examining these remnants, saw them as archaic etchings, enigmatic scripts, etched by an unseen force onto slabs hauled from Welsh slopes and Scandinavian quarries. In truth, those traces were organic, not scripted. Every line marked a colony, every colony a network of linked creatures. Each zooid acted as a sieve, extracting nutrients from surrounding seas. Graptolite colonies varied widely in shape. Some appeared shrub-like, with stems fanning out from a core like fern leaves. These bottom-dwelling types anchored to the ocean floor, sifting seawater while stationary, akin to bryozoans. They represented the primitive state, the foundation from which advanced variants arose. The floating graptolites ventured into freedom. During the late Cambrian or early Ordovician, select graptolite lines forsook the seabed for the vast pelagic realm. Their assemblies gained buoyant features, such as gas-filled floats known as pneumatophores or bubbly tissue clusters called nematophores, allowing them to hover in the water layers. They wandered with the tides, consuming any particulate organics the currents supplied, breeding and perishing without ever touching ground. This shift proved immensely thriving. Free-floating graptolites proliferated across the Ordovician, developing nest designs that bordered on mechanical precision. Certain types featured stems twisting around a main axis, helical configurations that rotated gently while afloat. Others displayed stems in a lined series, orderly rows evoking comb tines. Some pared down to a single or pair of stems, sleek profiles that cut through resistance. Didymagraptis ranked as one of the most striking. Its colonies featured twin stems dangling from a buoyant top, the setup evoking a tuning fork poised in the depths. Vast numbers of Didymagraptis drifted in Ordovician waters. Their Y-shaped outlines show up in strata across all continents, a worldwide emblem of the early to mid-Ordovician era. Graptolites served as the era's chronometers. Their floating communities evolved at a brisk pace. Fresh species emerged often, dispersed swiftly over global seas, and vanished after short geological intervals. A graptolite kind might endure just millions of years, occasionally fewer, before successors with altered forms took over. This swift cycling rendered graptolites invaluable for rock dating. Charles Lapworth, who established the Ordovician as a period, spearheaded their application in biostratigraphy. In the 1870s and 1880s, amid Scotland's southern highlands, he gathered graptolites methodically, recording species by stratum to create a timeline transferable to distant sites. Spotting a specific graptolite type in Scotland and the identical one in Wales meant those layers hailed from roughly the same epoch, laid down in parallel geological phases. The technique transformed stratigraphy. Prior to Lapworth, linking formations across areas relied on aligning lithologies or following visible beds over terrain. Afterward, fossils dominated correlation efforts. Graptolites proved particularly potent due to their drifting habits, scattering them worldwide. Identical kinds voyaged on flows from Laurentia to Baltica to Gondwana, imprinting matching fossils in deposits sundered by long-lost seas. Today's scientists continue relying on graptolites. The Ordovician splits into stages, each pegged to the debut of key graptolite species. Noting a specimen from the Darwinian stage invokes a graptolite-derived timeline rooted in the lineage of buoyant colonial beings extinct for 460 million years. Graptolites shared the plankton with many others. Acritarchs, those minuscule cysts encased in organic walls with ambiguous biological origins, had ruled the phytoplankton since the Proterozoic, likely acting as dormant phases for assorted algae. They functioned as safeguarding pods, enabling single-celled creatures to endure harsh conditions. During the Ordovician, acritarchs proliferated, their decorated exteriors growing increasingly complex, while their communities grew richer in variety, mirroring shifts in the surface layers of prehistoric oceans. Chitinozoans emerged in the Ordovician, flask-like organic forms possibly representing eggs from unidentified sea creatures. Their exact role is still under discussion, yet their stratigraphic value is well recognized. Similar to graptolites, chitinozoans underwent swift evolution, making them reliable biostratigraphic indicators. Their shifting morphologies documented the flow of Ordovician time. Radiolarians constructed silica-based skeletons, elaborate geometric lattices that settled onto the ocean bottom upon the creature's death, piling up in deposits that later turned into chert. The Ordovician witnessed radiolarian expansion, with skeletal designs becoming more intricate, a trend that persisted for another 500 million years. The drifting ecosystem formed distinct layers. Surface phytoplankton harnessed sunlight, transforming carbon dioxide and water into organic compounds via photosynthesis. Zooplankton hovered above and below, preying on phytoplankton or one another, passing energy along the food web. Bigger floaters such as graptolites sifted particles from the sea, introducing yet another feeding tier. This entire assemblage floated within the water column, ebbing and surging with daily cycles, carried by global ocean currents. Conodonts navigated this floating domain. For more than 100 years, conodonts ranked among the enigmatic fossils. They showed up as diminutive, tooth-resembling forms. Cones, bars, blades, and platforms made of calcium phosphate. Extracted in vast quantities from limestone, broken down by acid. Scientists employed them in biostratigraphy, appreciating their precision for rock dating, sorting them into species and genera, and tracing evolutionary lineages. Still, the creature behind them eluded identification. Each find intensified the puzzle. Conodont elements were unmistakably biological, crafted by some organism, organized into sophisticated arrays of interlocking parts. They displayed erosion marks hinting at a role in ingestion. They turned up in strata covering 300 million years, from Cambrian to Triassic, across all continents and marine habitats. Their maker thrived extensively and lasted long. The solution arrived in 1983. That year, scientists examining Carboniferous rocks from Scotland uncovered an extraordinary specimen, a full conodont organism. Delicate tissues survived beside the typical phosphatic parts. The animal resembled an eel, roughly 4 centimeters in length, featuring prominent eyes, a notochord, V-shaped muscle segments, and a tail fin. In its head, conodont elements formed a grasping and grinding tool for capturing meals. Conodonts proved to be vertebrates, or nearly so. Their exact spot on the vertebrate lineage sparks ongoing debate, but they were undoubtedly chordates, far nearer to humans than to any invertebrates. Those tooth-shaped features weren't true teeth, but parallel innovations, separately developed for comparable purposes. Ordovician conodonts stood as some of the group's initial and most varied representatives. They darted amid plankton swarms, their phosphatic gear snatching victims. Their serpentine forms twisted through seas that also cradled the earliest armored fishes. Two branches of primitive vertebrates coexisted in Ordovician waters. One fated to vanish by the Triassic, the other poised to claim the planet. You can grasp Ordovician plankton in your palm. Dark shales from Wales, Scandinavia, the Appalachians, or the edges of ancient Gondwana. Cleave them along, layering, and graptolites emerge in silvery gray against the ebony backdrop. Their forked patterns captured with stunning clarity. Even the tiniest traits stand out. Separate cups that once housed zooids, the stolons tying colony units together. The holdfasts securing certain types to buoyant wreckage. These fossils aren't scarce. Graptolite-rich shales abound to the point where affordable samples are available for purchase. Plentiful enough for geology classes to gather them during excursions. So widespread that galleries showcase hundreds. Beings that appeared fragile, fleeting, at the mercy of tides and breezes, forged a remarkably enduring fossil legacy. That durability stemmed from their existence. When planktonic life ends in the vast sea, it descends. Should it pass through oxygen-rich depths, predators devour it. Bacteria break them down further. Few remains make it to the ocean floor without damage. Yet, when they descend through oxygen-poor waters where decay processes halt due to lack of oxygen, these organisms can arrive at the sea floor largely unchanged. There, they might get buried in layers of fine sediment, eventually fossilizing as thin carbon layers within rock shells that future geologists will uncover on the hills of Wales. The Ordovician period featured vast anoxic regions. Factors like the warm greenhouse atmosphere, layered ocean structures, and the positioning of land masses that limited water mixing all promoted oxygen loss in deeper layers, setting the stage perfectly for graptolite fossils to endure. Those dark shales examined by Lapworth, which established the era's key divisions and remain standard references even now, stand as tributes to anoxia, chronicles of ancient seas starved of oxygen, where exceptional preservation occurred. As they floated, the graptolites outlined circulation routes hidden from bottom-dwelling life. Currents across the Ordovician oceans followed routes shaped by land configurations, prevailing winds, and planetary spin. In the Iapetus Ocean, which divided Laurentia from Baltica and Gondwana, distinct flow patterns emerged. Westward equatorial streams bumped against coastlines, curving into persistent gyres that spun without end. Graptolite groups hitched rides on these flows. Certain kinds stuck to specific water layers, while others roamed widely, appearing in any linked marine realms. The spread of these floating creatures uncovers clues to long-lost ocean dynamics. When graptolite types appear confined to specific areas, it signals blockages, currents that failed to link up, or isolated water bodies holding apart. Broad distributions, on the other hand, point to open pathways, flow networks that ferried drifters over vast expanses and deposited them far from home. Scientists decipher these spread patterns as if decoding ancient scripts, pulling insights on Ordovician marine flows straight from the bones of beasts that merely followed the tides. Unbeknownst to the graptolites, their journeys sketched out current maps. They simply existed, eating, breeding, perishing, their forms dropping into low oxygen depths to pile up in deposits that locked them away for eons. These wanderers bore witness to a dynamic sea, alive with swirling gyres and streams, sun-warmed shallows above chilly abysses, oxygen-laden shallows alongside lifeless troughs. Their petrified remnants capture that flux, etched eternally in rock, ready for interpreters to unravel the tales the waters inscribed. Amid the drifting plankton, feeding graptolites and conodonts prowling particulate haze, a shift approached from an unforeseen angle. Marine realms had become packed, stratified, elaborate. Organisms occupied almost all watery habitats. The upcoming major evolution demanded fresh territory. An advance was underway toward the coastlines, the lifeless stones and vacant skies of a realm untouched by biology. Continental surfaces lay exposed. Atmospheres hung devoid of breath. Across 4 billion years, the land masses stood as rocky wastelands. No root systems fractured the crust. No foliage snared the rays. No earth cushioned the shift from stone to sky. Just raw crystalline faces, battered by gales, shattered by ice, rinsed by downpours that returned no life matter to the waves. That desolation defies easy grasp for today's people. All peaks we've climbed wear mantles of growth. All gullies we've traversed bear the marks of root systems and plant cover. Ordovician land offered no such cover. They resembled alien spheres, desolate like Mars. Meanwhile, seas teemed for 3 billion years. Evolution had forged elaborate forms, varied gills, webs of breathtaking detail. Trilobites sported jeweled gazes, cephalopods stretched to 6 meters. Sifters erected stacked societies that filtered depths with machine-like precision. Waters brimmed with rivals, perils, pressures. Shores stood vacant. They lingered in anticipation. The colonization started via green algae. Chlorophyta had flourished in nearshore seas and inland waters since the Proterozoic. As light harvesters, they harnessed solar energy through chlorophyll, the pigment destined to tint every woodland and field worldwide. Certain branches had eased into intertidal habitats, enduring brief air exposure as waves receded and surged. Different groups had ventured into rivers and lakes, realms tougher than steady seas with shifting heats, variable chemistries, and ever-looming dry spells. Such edge habitats served as proving grounds. The strains enduring in splash zones and fleeting pools had already developed early counters to land's rigors. They withstood partial dehydration. They endured thermal shifts. These algae possessed the essential biochemical building blocks that would later form the basis for genuine land plants. Shifting from water-dwelling algae to plants on land meant tackling multiple issues all at once. Preventing dehydration stood out as the top concern. Air dries things out quickly, and any cell unable to hold onto its water would perish in mere hours once exposed. Managing gas exchange was just as vital. To perform photosynthesis, plants need to pull in carbon dioxide from the air. Yet, every pore that lets in that gas also lets out water vapor. Providing structural integrity presented yet another hurdle. In water, buoyancy supports organisms, so an upright growing alga in a pond would simply flop over from its own weight once out in the air. These adaptations emerged gradually across millions of years in evolutionary lines that barely left behind any fossils. Waxy cuticles evolved, covering plant exteriors with substances that repel water. Stomata emerged too, specialized openings that could widen for CO2 intake and seal shut to conserve moisture. Sturdy cell walls offered reinforcement, with lignin eventually adding the toughness needed for upright expansion. Each advance marked a modest increment, but combined they sparked a profound transformation. The earliest signs of land plants date to the mid-Ordovician, about 470 million years ago. No leaves, stems, or roots survive from that era. Those initial plants were minuscule, delicate, and not built to last, so their body parts rarely fossilized. What endures are their spores. These are reproductive units, genetic payloads wrapped in resilient shells that shield against drying and breakdown. Plants scatter spores into the surroundings, carried by wind or water. In suitable spots, they sprout into fresh plants. The spore casing consists of sporopollenin, among the toughest organic materials against chemicals. It withstands extremes that obliterate nearly all other life forms: intense heat, crushing pressure, chemical breakdown, and bacterial invasions. Spores outlast the parent plants, which decay away completely. Sedimentary layers hold these spores, particularly cryptospores, ones with shapes unlike any algal varieties, signaling origins in land-adapted plants. Such cryptospores show up in fossils from roughly 470 million years back. They first appear in Gondwanan deposits from areas now in Saudi Arabia, Libya, and the Czech Republic, then gradually spread to other land masses as plants evolved and migrated. The organisms producing these spores likely resembled today's liverworts, prostrate, ground-hugging forms that stick to wet spots without real roots or vascular systems, relying on surface water for breeding. By modern forest standards, they were underwhelming. A liverwort doesn't rise high. It offers no shade. It doesn't build woodland habitats or pump out global oxygen. It just grips soggy stones and scrapes by with bare essentials. Yet that bare minimum sufficed. From these humble origins, every form of land vegetation would arise. Jane Gray and William Shear reshaped our view of early terrestrial existence. Through articles in the 1980s and 1990s, Gray, a palynologist focused on ancient spores, and Shear, a zoologist examining primitive land arthropods, contended that land settlement started much sooner than experts had assumed. Traditional timelines slotted land plants into the Silurian and full ecosystems into the Devonian. Gray and Shear advanced the timeline, using cryptospores and fossil tracks to show colonization during the Ordovician. Their ideas sparked debate at first. The proof was circumstantial: spores absent their plants, tracks without creatures. Conclusions drawn from hints rather than intact remains. Skeptics claimed cryptospores could stem from water-bound life, and those tracks might come from beings that dipped into air but stayed aquatic. The argument raged on for decades, with fresh finds tipping the balance now here, now there. Lately, the evidence leans heavily toward an early takeover. Genetic studies using molecular clocks, gauging split times from DNA variances in today's species, routinely point to land plants arising in the mid-Ordovician or before. Ongoing cryptospore finds keep nudging the timeline earlier. Though science shuns total certainty, the prevailing agreement now supports an Ordovician start for land flora. Plants didn't venture onto land solo. Fungi tagged along, or maybe arrived ahead. The plant-fungus bond runs deep, potentially as ancient as land plants or even predating them. Today's plants team up with mycorrhizal fungi, their roots weaving through fungal threads that stretch farther to tap minerals roots couldn't reach unaided. In return, the fungus gets carbohydrates from the plant. In return, the plant supplies phosphorus and various minerals to the fungus. This mutual bond is essential, as the majority of terrestrial plants would perish without it. Traces of ancient fungi in the fossil record are scarce, given their delicate structures that seldom fossilize. However, biochemical signatures offer stronger proof. Unique fungal compounds show up in Ordovician rocks, indicating that fungal networks had already taken hold on continents by the mid-Ordovician. A few scientists propose that fungi ventured onto land ahead of plants, conditioning the ground and kick-starting the gradual buildup of soil that paved the way for advanced flora to thrive. The interplay among plants, fungi, and bedrock proved revolutionary. Plant roots paired with fungal hyphae bore into stone, releasing acids that break down minerals and carve passages for moisture and oxygen to infiltrate. As these life forms perish, their remains build up, blending with eroded particles to create earth. This soil holds moisture, holds onto essentials, and anchors bigger vegetation. The buildup happens gradually, requiring millennia to develop substantial layers, yet it presses on unyieldingly. Once underway, turning stark stone into a vibrant terrain becomes irreversible. Ordovician flora and fungi sparked this shift. They acted as trailblazers, the initial beings to approach desolate landmasses and spot potential where others saw barriers. The air responded to the shift. Through photosynthesis, plants turn carbon dioxide and moisture into carbohydrates and release oxygen. That oxygen drifts upward into the sky. Meanwhile, carbon gets locked away in plant matter, pulled from the air cycle for the plant's lifetime, and possibly entombed in deposits after death. Essentially, plants function as carbon extractors, siphoning out heat-trapping gases and substituting oxygen. Back then, the Ordovician air held roughly 15 times the CO2 levels of today. The warming from that was fierce, keeping poles free of ice. Early coastal plants were too few, too modest, and too confined to overhaul the air's makeup. Their impact stayed regional. A modest oxygen boost close to the surface, a minor CO2 dip right around active photosynthetic zones. Future growth would upend it all. Vast woodlands in the Devonian slashed atmospheric CO2 sharply, likely sparking glacial periods and undoubtedly reshaping weather patterns worldwide. The Carboniferous era buried carbon on an immense scale, forming the coal seams later mined and combusted by people, recirculating that old carbon skyward. The intertwined evolution of flora and air ranks among Earth's major balancing acts, with each shaping the other across eons. Those Ordovician pioneers marked the opening chapter. Unaware their lineage would overhaul planetary weather, raise woodlands spanning equator to poles, and produce the breathable oxygen for creatures They focused solely on pressing needs, sourcing hydration, harnessing sunlight, enduring on unforgiving stone. Ordovician plant remnants exist for those who search wisely. Cryptospores emerge from rocks via acid dissolution of samples, flushing out the rocky bulk to isolate the leftover organics. These spores are minuscule, mere micrometers across, demanding magnification to view. They lack the allure of showy relics. No grand displays in galleries or splashy illustrations in volumes. A simple tube of earthy, gritty residue fails to evoke the awe of a full trilobite or towering cephalopod casing. Still, such containers hold clues to a pivotal leap in life's saga. Shifting from seas to solids remade the world more than any other organic breakthrough. Today's land-based photosynthesis overwhelms that of oceans. Carbon tucked in upland greenery and dirt outstrips sea holdings by vast multiples. Root-driven erosion has revamped the elemental flows across the globe. It all stemmed from cryptospores in Ordovician silt, humble specks, everyday bits, harbingers of an upheaval, needing 100 million years to bloom fully. The verdant takeover was underway, though plants weren't alone in probing the watery edge. Those damp stones sheltering liverworts and fungi drew in seagoing guests too. Tiny arthropods with segmented limbs, ancestors of the bustling land dwellers to come. The inaugural beasts trailed plants ashore. They imprinted trails in the sands. Some 450 million years back along a vanished shoreline, an entity emerged from waves and traversed sodden muck. It created a path behind it, featuring paired indentations, the impressions left by segmented limbs pushing into the ground. This trace of motion got entombed, turned to stone, and safeguarded through time until a discoverer unearthed it and grasped its importance. These footprints go by the name protichnites. They show up in Ordovician sandstones across North America, formed at the edges of long-gone oceans. Every set of tracks shows two straight lines of tiny marks, occasionally joined by a middle furrow from a trailing body or tail scraping the ground. The design screams arthropod. Nothing else in nature yields such consistent matched patterns. A creature with a hard outer shell and jointed limbs must have produced them, some being stepped onto dry ground. The exact culprit behind the tracks remains a mystery. Protichnites might stem from various arthropod clans, perhaps eurypterids rising from shallow waters, or primitive myriapods probing the coastline, maybe crustaceans scavenging the tidal flats. No skeletal remains have turned up alongside these prints to pinpoint the maker. The creature stays unidentified, recognized solely through its steps, a spectral figure, etched in the dents it made. That unknown status doesn't lessen the impact. In the Ordovician, an animal trod upon land. Just that reality reshapes the tale of life on Earth. The ocean offered security. The shore brought peril. An arthropod, shifting from sea to atmosphere, hit an instant bodily emergency. Gills, which pull oxygen from liquid, falter out of water, their fine threads sticking fast. Their breathing capacity shrinks to nothing. A sea-dwelling arthropod ashore starts to choke in moments. Fixes like book lungs, windpipes, or alternative air breathers would arise down the line. Yet the initial shore explorers lacked any such traits. These were water-bound beings on short jaunts, heading back before breathing gave out. Drying out posed a comparable danger. Fluid slips away from bare skin, and a beast with a leaky outer layer sheds water fast in the open air. The oily sealed skins of today's land arthropods took eons to develop. The first visitors enjoyed mere basic shielding, their trips confined to damp spots, steamy atmospheres, or post-rain periods when humidity hung heavy. Gravity added yet another hurdle. The sea buoys up forms, a critter floating effortlessly in the deep senses, no burden from its bulk. The identical being on solid Earth has to support its entire load on limbs built for paddling or padding over mushy bottoms. The upgrades for land travel, tougher knee joints, sturdier shells, reworked muscle points, came about slowly, with each wave of offspring a touch more suited than before. Those pioneer land arthropods didn't conquer any of these issues outright. They coped with them briefly, halfway, enduring quick dashes prior to diving back into the waves. The beach served as an edge, not a base. What drove them from the depths in the first place? No one explanation covers it. Various branches likely faced unique urges, varied survival strains, nudging them to the divide between realms. Clues arise from ancient bones and observations of today's semi-land arthropods. Sustenance probably lured many. The tidal band gathered plant scraps, withered seaweed, beached life, wave-tossed waste. A tolerant forager could tap supplies beyond the reach of full-time swimmers. The dawn of land-based food webs likely hinged on munching such scraps, picking at leftovers instead of nibbling live growth, feeding on the ocean's cast-offs. Fleeing hunters might have spurred others. The Ordovician waters teemed with threats, stalked by cephalopods, eurypterids, and more. A swimmer able to exit briefly gained sanctuary in a zone those hunters couldn't chase into. The mainland was unforgiving, yet barren. No stalkers roamed the sands, no fangs lurked by the stones. Mating habits could factor in, too. Certain current arthropods deposit eggs beyond the surf, shielding them from sea foes, water-loving molds, marine perils. Should Ordovician arthropods have mirrored that, their breeding needs would favor grown-ups fit for land trips, if only to place eggs in secure spots. These forces intertwined and amplified one another. As certain members started using the shore, nature picked for those fitter to last there. Generation by generation, they edged the limit outward, enduring extended stays, straying deeper from the surf. Tuning sharper to a world sealed off from beasts for 4 billion years. The fossil evidence for Ordovician terrestrial creatures remains disappointingly thin. Footprints like those from Praticnites and other such ichnofossils point to arthropods roaming the land. Yet, actual body remains are virtually non-existent. Environments that could fossilize land-dwelling life were scarce. A creature perishing on shore faces rapid breakdown from decomposition, predators, erosion, and the relentless elements above the waves. Preservation demands unusual events, swift entombment, oxygen-poor settings, or mineralization, and such conditions rarely occurred in the ancient continental landscapes. It wasn't until the Silurian and Devonian eras that truly remarkable land fossils emerged. Millipedes, scorpions, primitive insects, and the initial arachnids. These discoveries from later times reveal that, by the Ordovician's close, land arthropods had already diversified and taken hold firmly, hinting at a colonization effort spanning dozens of millions of years. The Ordovician footprints align with this chronology, implying initial cautious forays onto solid ground happened right in that epoch, even without lasting skeletal traces from those trailblazers. Genetic data reinforces this early shift. Analyses of DNA among contemporary arthropods indicate that key land groups, myriapods, arachnids, hexapods, split from ocean forebears in the Ordovician or soon after in the early Silurian. Though molecular timelines lack precision and their tuning remains debatable, they reliably indicate a start rooted in the Ordovician for animal life on land. The clues align despite gaps. Impressions sans skeletons, genetic estimates lacking bones, deductions absent concrete evidence. The narrative feels patchy, blurred, and vexing. Still, the broad shape emerges distinctly. During the Ordovician, creatures started claiming the shores, trailing the vegetation that arrived first, launching the settlement that would birth every land-based community on the planet. The alliance between flora and fauna didn't form overnight. Initial land plants stayed close to the damp ground, forming low mats with scant architecture for beasts to use. A simple liverwort provided no refuge, no high vantage, no intricate niches. That primeval shore world was basic. Films of microbes, scattered clumps of basic greenery, exposed stone in between. No woodlands to dwell in, no fallen debris for cover, no treetops to scale. Over subsequent ages, plants and animals would evolve together, each fostering niches for the other. Vegetation would rise higher, offering layered spaces for creatures to navigate. Beasts would turn plant eaters, consuming foliage while developing jaws, suited for slicing and mashing greens. In response, plants would craft protections, poisons, spines, rigid tissues, and animals would devise ways around them. This escalating contest would propel both toward richer forms. The Ordovician witnessed none of that intricacy. The terrain was plain and scattered, a realm in its infancy of life's expansion. Arthropods traversing Ordovician coastlines scavenged mostly tidal cast-offs for sustenance. They were trailblazers in a wild expanse, heavy on trials and light on gains, rich in perils over prospects. Nevertheless, they endured, one brood at a time. Certain ones braved the dry, endured to breed, and passed on traits a touch more suited to the shift. This gradual change unfolded across eons, yet proved unstoppable. Life had seized the landmasses. It would never yield. Contemporary shorelines echo that Ordovician rhythm. Horseshoe crabs haul from the surf to deposit eggs in the dunes, their primordial forms unaltered over vast stretches of time. Ghost crabs dart amid their holes, with air-capable gills but needing dips in water now and then. Hermit crabs probe beyond the high tide mark, probing the divide of sea and soil. All these beings revive the pivot that ignited in the Ordovician, showcasing the habits and bodily limits that enabled the move. Such coastal zones serve as active test sites, organic trials of the ocean-to-dry progression. The hurdles for today's semi-aquatic arthropods, drying out, breathing, bearing their weight, mirror those of the Ordovician vanguard. Their fixes remain identical, hugging watery edges, dodging peak sun, hunting damp hideaways, withdrawing amid harsh spells. The strategy dates to 450 million years back. Today's species adhere to it. Shifting from ocean to earth wasn't one leap, but an ongoing spectrum of changes, haltable at any stage. Certain lineages completed the leap, their heirs entirely landbound with forms wholly tuned for aerial existence. Certain creatures linger at that edge, relying on water for key aspects of their existence, while remaining bound to the divide between habitats. The Ordovician tracks capture an initial phase of this shift. It marks a time when the earliest animals probed the divide, discovered its passability, and started venturing across. The landscape was evolving. Surfaces once covered only in bare stone and microbial layers were developing into something new, a fragile layer of organisms, uneven and limited, yet unmistakably there. Vegetation adhered to damp areas. Fungi wove through cracks. Arthropods imprinted trails in sediments destined to harden into rock. The land masses were no longer barren. They had been settled, occupied, altered in manners that would intensify over future eras. The settlers couldn't foresee what loomed ahead. From their vantage amid the stones and basic flora, the heavens appeared ordinary, azure or overcast, serene or stormy, the unchanging canopy that had spanned the globe for eons. They couldn't detect the accumulation in those skies. They couldn't grasp the expanding swarm of fragments encircling their world. Far overhead, beyond the scuttling arthropods and anchored greenery, an astonishing phenomenon was forming. Our planet was acquiring a ring. Andy Tompkins wasn't searching for such rings. His focus was on craters. Specifically, impact craters. The wounds from asteroids or comets slamming into Earth, carving out kilometers-wide depressions, incinerating stone, and etching enduring traces in the geologic record spanning hundreds of millions of years. At MES University in Melbourne, Tompkins, a geologist, examined the Ordovician impact history within a larger study of asteroid strikes across Earth's timeline. Initially, the figures appeared typical. 21 verified craters from the Ordovician era dotted various landmasses, laid down across 42 million years. Their spread seemed haphazard. Nothing special, just the sort of pattern you'd anticipate from cosmic junk plummeting from assorted angles and moments. But then Tompkins overlaid them onto a paleogeographic chart. This reconstruction depicted Earth during the Ordovician, with land masses in their primordial layouts before tectonic forces rearranged them to today's setup. Laurentia straddling the equator, Gondwana in the southern hemisphere, Baltica and Siberia, positioned amid the standard ancient assembly, known to deep-time specialists. The craters didn't distribute evenly. They aligned in a streak, a zone stretching eastward across the chart, tracing the equator with an accuracy too precise for mere coincidence. All 21 confirmed Ordovician impacts, amassed over vast timescales, had landed within 30 degrees of the ancient equator. Most hit inside 15 degrees. A few struck within 5 degrees. Tompkins crunched the numbers. The odds of such tight grouping happening randomly stood at roughly 1 in 25 million. An influence had steered the strikes toward the equator. It functioned like a magnet, pulling in orbital rubble to a particular band of latitude, yielding a strike pattern defying explanations from scattered origins like the asteroid belt, Kuiper belt, or elsewhere in the solar system. In September 2024, Tompkins and his team unveiled their theory in Earth and Planetary Science Letters. The article, Evidence for a Massive Short-Lived Planetary Ring System Around Earth During the Ordovician Period, proposed that Earth once had rings akin to those of Saturn, Jupiter, or Uranus. For tens of millions of years in the Ordovician, our world hosted a ring network. That system showered fragments downward in a focused equatorial assault, scarring the surface from Australia to Sweden, along lines that once lay under a Saturn-esque girdle of pulverized stone. The idea was bold, the data persuasive, the ramifications profound. It all traces back to an asteroid around 466 million years ago, in the early mid-Ordovician as marine life underwent major changes, when trilobites blanketed ocean beds and enormous cephalopods prowled the depths. This asteroid hailed from the inner solar system. Sizable, maybe a few kilometers wide, it mainly consisted of L-chondrite, a prevalent stony meteorite type, making up about 38% of today's falls. These feature modest iron levels and distinctive mineral mixes that aid identification. The body wasn't on a crash course. Its path skimmed by Earth, near yet not near enough to collide. A close shave, the routine gravitational brush in the solar system that typically passes without incident. On this occasion, repercussions followed. When the asteroid ventured too close to Earth, crossing a threshold known as the Rho limit, powerful tidal forces started ripping it to shreds. The portion nearest to Earth experienced a much stronger gravitational tug than the opposite side, creating differential stresses that overwhelmed the body's structural integrity. The material cracked, broke into pieces, and broke down entirely into a swarm of rubble, from massive boulders the size of buildings down to fine dust particles. This Rho limit takes its name from Edward Roche, a French astronomer of the 19th century, who determined that any body mostly bound by its self-gravity would disintegrate upon getting too near a larger mass. The precise separation varies based on the densities involved. In the case of a rocky asteroid nearing Earth, that key distance sits around 9,500 kilometers from the planet's core, or roughly 3,000 kilometers up from the surface. Breaching that barrier caused the asteroid to explode into fragments. While most of the wreckage veered off on separate paths, dispersing into orbits that would eventually sweep bits far from Earth. Certain chunks plummeted right away, streaking through the air, slamming into the ground and carving out impact sites. A significant portion, likely the bulk, of the asteroid's remains settled into a stable path around the planet, forming an encircling band of detritus that spanned thousands of kilometers across the void. In this way, Earth gained its own ring system. Scientists have a solid grasp on how planetary rings work for over 400 years, since Galileo's 1610 telescopic sighting that led him to think Saturn sported planetary ears. Those famous bands have been under scrutiny. Missions like Voyager and Cassini have delved deeply into Saturn's rings, analyzing their makeup, monitoring their movements, and charting their changes. Jupiter, Uranus, and Neptune each have their own, more subdued and dim rings, yet all operate under identical rules. These features typically lie in the planet's equatorial plane, herded by gravity into a thin, flat disk matching the world's spin. Made up of bits from microscopic dust to rock chunks as big as boulders, they feature individual particles tracing their paths, with group effects generating ripples, voids, and patterns detectable from afar. On vast geological timescales, rings prove fleeting, gradually expanding outward or spiraling inward, fading away over eons via crashes, air resistance, and orbital nudges. Earth's new ring would have behaved similarly. It would manifest as a debris disk, hugging the equator, appearing from the ground as a vivid streak arcing through the heavens, most striking at sunrise and sunset, when the sun's rays caught the particles just right. This display would outdo what Saturn's rings look like up close, thanks to the nearer proximity, greater thickness, and unweathered freshness of the material, which hadn't yet dulled over time. At the equator, it might seem like a slender slash dividing the sky, bowing from one edge of the world to the other, narrow in profile but radiant enough to eclipse the starry Milky Way. Farther north or south, say at 30 degrees latitude, the view would widen into a more substantial arc, its tilted perspective unveiling the disk's true form. From the poles, someone gazing outward would behold the entire setup as a luminous loop girdling the globe, like a glowing wreath atop the world. But no humans were around to take it in. The grandeur went unnoticed by trilobites, cephalopods, and life forms too basic for awe. It gleamed overhead in atmospheres untouched by eyes built for such sights. A grand show, performed for filter feeders, sediment scrapers, and beings whose perception stuck to scent trails and tactile cues. Still, the ring couldn't endure indefinitely. Planetary mechanics ensure nothing does. Across millions of years, the circling rubble steadily rained down. Drag from the thin upper air, tugged the tiniest grains earthward, where they flared as shooting stars, depositing layers of vaporized stone in a soft cosmic drizzle. Bigger fragments endured the fiery descent, striking land and sea to gouge basins that would hold the scars of this onslaught for hundreds of millions of years. These strikes weren't scattered everywhere. Debris locked in equatorial paths, drops toward equatorial zones. The laws of motion demand it, no exceptions. An equatorial orbiter, dragged down by air friction, orbital wobbles, or gradual slowdown, must ultimately hit somewhere along the middle latitudes. Thus, a ring girding Earth's waist could only pepper the equatorial belt with craters. That was the revelation Tompkins uncovered. The 21 Ordovician craters showed no random spread because they stemmed not from haphazard cosmic wanderers but from this targeted fallout. These fragments formed a debris ring, remnants of an asteroid that had circled Earth for eons before disintegrating into a focused barrage along the latitudes directly under the ring. Proof for this idea goes further than just the crater's layout. Ocean floor deposits from the Ordovician era show higher levels of L-chondrite substances. These layers built up across the globe, gradually covering the fossilized shells of brachiopods, trilobites, and graptolites, intertwined with alien remnants like chromite particles, platinum group metals, and mineral patterns typical of L-chondrite makeup. The levels surge right in the mid-Ordovician, precisely when the ring would have been shedding debris onto the world. That surge is known as the Ordovician meteor event. It shows up in ocean bed samples from scores of sites, marking a worldwide sign of intensified meteor strikes that persisted for tens of millions of years. Earlier scientists had noted this surge, identified it as proof of abnormal impacts, and suggested causes like asteroid belt clashes or a big meteoroid's fragmentation. Tompkins's theory offers a clear process. The material wasn't coming from the asteroid belt, but from Earth's own orbit. It described the slow breakdown of a ring system, unloading its contents onto the planet, at rates far exceeding typical influx. The timeline matches perfectly. Such rings fade over millions of years, neither mere thousands nor endless billions. Experts believe Saturn's rings are recent, maybe just a couple 100 million years old or even less, and they're steadily shedding mass as bits spiral in or flee out, the entire setup quietly dissolving. Earth's Ordovician ring likely took a comparable path, enduring 20 to 40 million years from its birth to full dispersal, aligning with the span of the Ordovician meteor event etched in sea deposits. The crater's dates bunch up in the mid to late Ordovician, around 465 to 450 million years ago. They're not evenly spread. More dots in the earlier phase of that window, implying peak strike rates soon after the ring's creation, tapering off as it thinned. This lines up with how rings behave, starting with thick clusters of big chunks that spread and dwindle over time. From the ground, you might have spotted the ring yourself. Picture standing on an Ordovician shoreline, along Laurentia's balmy tropics or Gondwana's milder edges, and gazing skyward. The air is crisp, the sun dipping low, hues shifting from azure to deep purple. As night creeps in, a glowing streak emerges, slicing the sky from horizon to horizon, slimmer than your thumb at arm's length, yet outshining every star. It's the ring, a stream of circling rubble snagging the sun's dying glow, shining through dusk, lingering long after twilight and returning just before sunrise. The moon climbs its pale shine, softening the ring's gleam without hiding it entirely. Closer than the moon, the ring varies, brighter where debris packs tight, dimmer in voids sculpted by gravity's pull. Intricate, and striking, even if no one was there to call it beautiful. Certain evenings shooting stars blaze more often than normal, as ring bits plunge in bursts beyond the usual trickle. Now and then heftier chunks pierce the air, sparking blazing orbs that throw shadows, booms that shake the depths, and strikes that gouge new pits in the warm coastal flats. The barrage comes in fits and starts, erratic, sometimes devastating. The ring would have influenced the weather, no doubt. Tompkins's article treads lightly, noting the unknowns, yet the core science is unavoidable. Rings obscure sunlight. The blockage hinges on optical depth, the share of light snagged by grains versus slipping past the spaces. Saturn's bands differ in density, some almost solid, others see-through. Earth's, built from raw stone fragments, would have been fairly dense overall, especially in its thickest zones. The shade hits the equator. Orbiting in Earth's waistline plane, the ring would drop its darkness straight down to the middle latitudes, dimming warmth, cutting solar reach to the surface, and reshaping weather flows. The chill peaks at equinox, sun aligned with the equator and beaming right through the ring's layer, shadow at its sharpest. During solstice, with the sun offset, northward or southward, the shade slides, the impact milder yet ongoing. Just how much cooling occurred remains open to debate. Tompkins and his team suggest that such a ring could have diminished heat retention at the equator by a few percent, sufficient to cause a measurable drop in temperatures, influencing ocean currents and impacting life forms reliant on the consistent warmth of tropical waters. Some scientists, however, doubt if the impact was significant enough to show up in geological traces, if supporting data aligns with the proposed timeline for cooling, or if other factors better explain the detected climate variations. The discussion persists. This idea, introduced in 2024, continues to face scrutiny through evidence, gathering both backing and challenges. Scientific progress is deliberate and careful, demanding various independent proofs before embracing bold assertions. Proposing a ring encircling our planet qualifies as bold. Yet supporting data is building. The outcome remains undecided. What stands out clearly is an oddity in the Ordovician era. Impact patterns are irregular. Meteor arrivals were elevated. Crater placements resist simple chance-based models. Time will reveal if Tompkins's view holds, if our world once bore rings, if the resulting shade chilled the globe, and if those weather changes played a role in the mass die-off that closed the era. Currently, this theory ranks among the most striking ideas in contemporary planetary studies. For a short geological moment, Earth might have mirrored Saturn. A ring adorned the heavens. The equatorial belt experienced its dimming. Ancient stones hold the scars of those strikes, etched into craters overlooked for 460 million years, until their arrangement caught attention. Tompkins spotted the arrangement, unveiled to a mind viewing the records from an apt angle, charting craters on suitable projections, posing key inquiries. Breakthroughs frequently unfold like this. Clues lingered eternally, overlooked until the proper gaze revealed them. The ring has vanished. Its final pieces descended eons past, incinerating in the air, scarring the ground. Merging into the swelling layers of seabed deposits on Ordovician ocean beds. What's left are deductions, numerical evaluations, and the diligent efforts of Earth scientists examining crater spreads, meteor makeup, and layered strata. Long ago, the firmament differed. A luminous arc spanned above, seen from all landmasses, most vivid near the equator, dimming as it neared the poles. Rubble showered steadily for millions of years, riddling terrains with pits, sprinkling seas with alien particles, reshaping weather patterns that possibly sparked disaster. Far over the lands where early arthropods practiced air-breathing, far above the waves where trilobites foraged and cephalopods roamed, the ring shimmered in borrowed sunlight. Bits clashed, broke apart more, twirled lazily earthward. The pelting persisted, intensified, crested, and gradually waned as the ring dispersed and faded. Meteor displays lingered on. In truth, they were just starting. Limestone archives the tale. Extract a core from seafloor buildup from the mid to late Ordovician. Layers formed slowly across millions of years on primordial ocean bottoms. Examine their makeup. Amid the calcium carbonate from shells, the silica relics of radiolarians and sponges, the silt borne from far-off lands, lies an intruder. Chromite specks, minuscule crystals of chrome iron oxide, with traits unlike any earthborne material. Their space origins are indisputable. They came via meteoroids that disintegrated during atmospheric entry or shattered upon striking. They drifted down through the depths, piled on the bottom, integrated into deposits that hardened into the limestones and shales experts dissect today. In Ordovician layers, chromite levels hit about 100 times normal rates. 100 times. No faint rise, no mere data quirk. No need for intricate scrutiny to spot. The surge is blatant, striking. A clear marker, emerging from sites in Sweden, China, Scotland, Russia, and spots worldwide. In every mid to late Ordovician marine deposit examined by geologists, the identical trend appears. Heightened extraterrestrial debris, persisting across tens of millions of years. This marks the ring's footprint. Orbiting fragments plummeting, blazing up in the sky, scattering once asteroidal dust onto seas after circling Earth for ages, finally descending in volumes that dwarfed typical cosmic dustfall. This onslaught stretched on without respite, fierce and unyielding, a barrage of meteors enduring far beyond the span of human history, outlasting our species' time on Earth, surpassing the length of typical glacial epochs, some 40 million years of ceaseless flames. To grasp the scale, consider the baseline. In everyday circumstances, our planet gathers around 40,000 tons of cosmic matter each year. Much of it consists of tiny dust specks that glide softly into the air layers without igniting, layering quietly into dirt and seabed layers too subtle to notice. Bigger chunks, like those the size of pebbles or fists, ignite into shooting stars during predictable yearly displays that stargazers eagerly observe. Now and then a heftier object punches through the air, slams into the ground with force enough to carve out a pit. This inflow remains even, foreseeable, and utterly routine. Over eons past and into the distant future, orbital scraps have steadily dripped into our world's pull, a process spanning billions of years. But the order of vision shattered that rhythm. At the height of the ring's breakup, the rate of meteoroid drops could have surged by 100 times or greater. Rather than 40,000 tons yearly, imagine 4 million tons a year, 10,000 tons daily, 400 tons hourly. A non-stop cascade of celestial junk onto a world whose air envelope couldn't handle the load. The heavens must have glowed with fiery trails. Not just sporadically, or when our path intersected a comet's scattered remnants, but without pause. Night after night turned into a meteor display. Any cloudless dusk brought a show of darting glows, blazing orbs, and the telltale signs of ring fragments plunging through the sky. The bulk of these arrivals were mere grains and stones, bits that flared out entirely in the air, contributing their substance as gases and powdery remnants high up. Those chromite specks in the deposits originated from such minuscule fallout. Leftovers from innumerable minor meteoroids that had incinerated during descent. Every speck stood for a speck that had circled the globe, plummeted airward, sunk into the seas, and ended up entombed with the husks of sea life, oblivious to the inferno overhead. The heftier fragments made for grander spectacles. A rock, the size of a boulder streaking in, unleashes power akin to multiple tons of TNT. Its blaze lights up the terrain below, throws shadows and shines for hundreds of kilometers. The blast shakes buildings, shatters panes, if such things existed, and echoes noises that span whole landmasses. Should the piece hold together to strike, it digs a basin, hurls rubble far and wide, and sparks a nearby disaster. In the ring's unraveling phase, incidents like these might have struck every month or week, even more often at the frenzy's crest. Earth faced siege, not from stray belt wanderers, but from its encircling band as fragments methodically purged themselves via air friction and orbital fade through basic mechanics. The pits that endure capture the mightiest strikes. 21 verified Ordovician impact sites stand confirmed. All trace a line along the ancient paleo equator, all timed to the ring's dispersal window. These mark the heaviest hitters, the slabs robust enough to weather the air, holding speed and bulk to gouge marks still readable after 460 million years. The grandest verified Ordovish pit is Lochna in central Sweden. The strike hit about 458 million years back. It hollowed a 14-kilometer-wide hole, unleashing force like several million tons of TNT. The culprit likely measured 600 meters to 1 kilometer wide. A hefty space rock indeed, capable of widespread ruin, yet minor on a global scale. Lochna had company. Siljan, likewise in Sweden, spans 52 kilometers, although its Ordovician link draws debate. Tavaren, Granby, and various lesser sites dot Scandinavia and farther afield. Each pit signals a ring chunk's landing, each depression a wound from the onslaught. Their spread reveals much. The land that grew into Scandinavia lay close to the equator then, smack under the ring's direct drop zone, drawing an outsized barrage. Fellow low-latitude zones echo the trend. Australia, hugging the equator at the time, hosts multiple Ordovician craters. North America's old heart, spanning the subtropics, carries strike marks from that era. The pummeling lacked chance, it defied randomness. Impacts originating randomly from the asteroid belt would lack any bias toward specific latitudes, pummeling the entire planet from the poles to the equator with uniform likelihood. Yet the clustering around the equator points unmistakably to debris, originating from a ring where fragments plummet from orbital paths confined to those low-latitude zones. The creatures enduring this onslaught lacked the awareness to grasp the events unfolding above. Picture a trilobite scuttling over an Ordovician seafloor, a cephalopod pursuing prey amid the water layers, or a brachiopod sifting nutrients from the flowing currents. None had the mental faculties to detect celestial trends, to observe how shooting stars multiplied in frequency, or to link those vivid trails in the heavens to the sporadic jolts that rattled the ocean bottom and unleashed waves surging over continental shelves. They endured the consequences without fathoming the origins, heightened influxes of silt from airborne particles, shifting illumination if dust built up thickly, and sporadic disasters from close strikes that upended local habitats. The ring's gradual breakup imposed a lingering strain, an ongoing disruption of everyday stability that stretched across durations far beyond any single lifespan, yet concise enough to register clearly in rock strata as a defined episode. Ocean floor deposits captured the proof. In the Ordovician basins, layers piled up relentlessly from the remains of expired shells, waste from zooplankton, eroded clays off land masses, and lime secreted directly from the briny depths. Chromite particles tumbled in alongside it all, blending into the accumulating matrix and etching themselves into Earth's history. Their abundance crested midway through the Ordovician and tapered off afterward. Initial analyses of this surge, predating Tompkins's ring theory, chalked it up to a smash-up among asteroids in the primary belt, the elchondrite progenitor shattering, hurling chunks toward the inner realms of the solar system, with portions ultimately crossing paths with our world. That view covered the boosted influx of space rocks, the event's prolonged stretch, and the elchondrite makeup. Tompkins's idea introduces a vital twist. The rubble didn't streak straight from the belt. It got snared into a temporary orbit, coalescing into a ring that encircled Earth for eons prior to raining down. This setup accounts for the equator-focused scarring, outperforms direct paths in justifying the drawn-out shower, and offers a way to funnel strikes into a slim zonal strip. The data backs this upgrade. The chromite uptick starts just ahead of the earliest verified craters, aligning with the ring assembling before the big hits landed. Crater timelines overlap the phase of maximal chromite levels, tying both to the ring's unraveling. The sequence holds together solely if the fragments looped around Earth instead of hurtling in from afar. Back then, the heavens looked alien, riskier, grander, brimming with signs that the void isn't vacant, that solar neighborhoods harbor rubble, that paths erode, and that pull of gravity drags unyieldingly earthward. Imagine standing along an Ordovician coastline at the height of the onslaught. The sun dips below the horizon, nightfall creeps in, and the ring materializes, that glowing arc slicing across the firmament. It gleams more intensely this evening, fed by new influxes, while patches fade where bits have lately plummeted. With deepest dark settling, fireballs start flashing, one popping up every minute or so initially, building to a steadier rhythm, some dim and fleeting, others flaring so fiercely they light up the terrain for moments. A handful blaze with such intensity they throw several shadows, their glow bouncing off the vast, shallow waters, submerging ancient landforms. The spectacle unfolds across the night. Certain streaks trace ring shards whose paths have eroded to meet the air. Others stem from knockoffs, bits chipped loose in clashes, their courses scrambled by blows that splinter big chunks into clouds of tinier survivors. Ring mechanics spawn chains of events. Strikes generate scatter. That scatter smacks into remaining ring stuff. Shattered remnants spiral down quicker than whole bodies. The setup hastens its collapse. It builds momentum. Extra bangs yield extra fine debris. Extra fines boost the drag from air exposure relative to weight. More drag speeds the plunge. Thus, the ring unravels in an explosive curve once underway. Its span clocks in at mere millions of years, not billions. Its endgame could dazzle as holdouts slam home in a quickening torrent. It's unclear if the inhabitants of the Ordovician era ever saw such a dramatic conclusion. The evidence from craters reveals no clear surge during any specific interval. There's no abrupt flurry of collisions signaling a disastrous ring breakdown. Instead, the dispersal unfolded steadily across tens of millions of years, more like a persistent drizzle than a fierce downpour. Maybe the ring just grew fainter until the leftover bits were too scattered to leave detectable marks. The final specks likely dropped without fanfare, blending into the routine stream of cosmic particles. Eventually, the impacts ceased. Levels of chromite in ocean sediments normalized by the late Ordovician. The most recent verified craters linked to the ring's fading date back to about 450 million years ago. The heavens brightened. The ring slipped from sight. With its fragments dispersed and its influence ended, the 40-million-year spectacle in Earth's atmosphere drew to a close. All that lingered was the planet's rocky archive. Traces of chromite and limestone basins lined up with forgotten latitudes, elevated platinum group elements in seafloor deposits. These faint chemical and structural clues enable scientists today, eons afterward, to piece together the events, spot the recurring motifs, and advance theories that once sounded preposterous until the data compelled them. Earth once bore rings. Those rings dissolved. The atmosphere glowed from impacts for 40 million years. The stones hold the tale no creature observed with awareness. No watcher documented save via the quiet buildup of rubble in layers and the carving of basins in bedrock. The meteor showers eased at last. The remnants plummeted. Chromite traces ebbed back to baseline. The atmosphere lightened. The ring almost vanished. Just the thinnest traces of rubble in fading paths, lingering for a few more million years. Still, the ring's deepest legacy might not lie in the pummeling. A different change was underway, one reshaping the globe's weather entirely. The shadow chilled the environment. Sunlight can't penetrate every spot. A ring circling Earth's midsection throws darkness across the tropical zones. The setup is inevitable, dictated by the rules of orbits and light's path. The sun arcs from different positions over the seasons, overhead at the equator during equinoxes as it aligns with the sky's midline, shifted poleward at solstices. Yet during equinoxes, the sunlight threads through the ring's plane, draping the shadow straight onto the ground beneath. The darkness isn't total. Viewed from Saturn's upper layers, its rings project intricate shadows, bright streaks where spaces let rays pass, dim streaks where dense parts eclipse them. Earth's hypothetical ring likely mirrored that pattern. Zones of varying light-blocking thickness, shifts in darkness, strength tied to particle clusters. Overall, though, the impact meant dimming, fewer sunbeams hitting the equatorial belt, cooler air in spots right under it, disrupted airflows as the heat divide between dimmed tropics and sunlit subtropics spurred gusts, shifted sea streams, shuffled warmth and patterns beyond what partial data lets models capture fully. The extent is still contested. Tompkins and team propose the ring-cut equatorial sunlight by a modest amount, say 2 to 5%, sufficient to drop land temperatures by 1 or 2 degrees Celsius in hardest-hit areas. Some experts argue for bigger shifts, others for tinier ones. The ambiguity runs deep due to shaky data on key factors. The ring's light absorption, its spread outward, particle sizes, the peak shadowing span. One thing stands out. Cooling took place. Ordovician records trace a shift from balmy greenhouse states to chillier phases midway and late in the period. Oxygen isotopes in ancient shells mirroring the sea's warmth when they grew show steady temperature drops. Carbon isotope swings hint at reworked sea flows and life output. Rock layers signal rising ice cover, peaking in the Hanantian glaciation at the era's close, one of the harshest freezes in Earth's past. The puzzle centers on the ring's shadow's role in this chill. Did the equatorial light cut spark chain reactions that boosted the effect, nudging the world into ice? Did this unplanned band, guided solely by pull-in paths, unwittingly redirect the planet's weather saga? The idea ventures into guesswork. In his 2024 paper, Tompkins openly recognizes this point. Linking the shadow cast by the ring to the era's climate, chill makes sense, aligning with our understanding of how planets manage energy, and bolstered by the matching timeline. The ring broke apart during the exact period of that cooling trend. Still, establishing a direct cause and effect link from mere timing is tough, maybe even out of reach, given that these happenings date back almost 500 million years with only indirect clues to go on. Weather patterns are intricate. Numerous elements affect worldwide temperatures. The Ordovician chill might have stemmed from drops in carbon dioxide levels in the air, alterations in how oceans flowed, the erosive impact of fresh mountain ranges rising up, or the initial spread of plants onto land masses, which started reshaping the way carbon moved through the environment. Among these various influences, the ring's shadow might have played a supporting role, not the only force at work, but one piece in a larger mix of circumstances that collectively nudged the global climate into a different phase. Sorting out how much each element contributed is a common hurdle for researchers examining modern shifts in weather. It turns into an almost impossible task when looking at changes from 450 million years past. With no chance for hands-on data collection, limited and unclear stand-in evidence, and land masses and seas arranged in ways far removed from today's setup, the shadow descended and temperatures fell. Did these two developments truly influence each other, or was it just chance? That's still up for debate. Think about the science behind shading at the equator. No other zone gets sunlight as straight on as the equator does. Around noon, the sun hangs almost directly above, beaming down at angles near 90 degrees to hit the ground with the highest energy punch per square unit. That's the reason tropics stay hot. Dense forests huddle close to the middle latitudes, and seas there run the hottest anywhere. Cut back even slightly on that solar input, and the whole heat equilibrium tilts. Air movement in the atmosphere relies on differences in warmth. Hotter air climbs, colder air drops. Those pressure imbalances spark breezes. Near the equator and tropical zones, heated air lifts off and heads toward the poles high up, losing heat along the way before dropping back down around 30 degrees north or south. Known as Hadley cells, this setup shuttles warmth from the center out to the edges, eases wild temperature swings, and powers the steady trade winds that have guided mariners for ages. Dimming the equator's heat saps strength from this loop. Less sun on the surface means the overlaying air heats up slower, ascends with less force, and carries away fewer calories poleward. The entire system of air currents dials down. Breezes ease off, heat flow drops. Areas in the middle latitudes get less tropical warmth and chill accordingly. Ripples of this change spread across the weather network. Seas shift in parallel ways. Expansion from warm equatorial waters forms a minor swell in ocean height, pushing top-layer flows outward from the center. As things cool, that equatorial sea temperature dips. The swell evens out. Flows lose momentum. Heat, heading to the poles, slows. Farther reaches get less warmth. Polar zones drop further in temperature. Ice starts building up. Ice boasts a high albedo. It bounces back rays instead of soaking them in. Worlds with greater ice extents and more sunlight right back into the void. This leads to even more cooling, building more ice, which bounces back yet more light. That albedo ice loop stands as a top amplifier in climate studies, able to propel a world from mild weather to widespread freezing once it kicks off. The Ordovician wrapped up in ice. The Hernantian glaciation, named after the Hernant Valley in Wales, brought huge ice caps across Gondwana, which had by then slid toward the South Pole. Oceans shrank by roughly 70 to 100 meters as liquid turned solid and froze away. Low-lying warm waters pulled back from the flooded shores of land. Sea life communities, which had flourished in steady, balmy settings for many millions of years, suddenly grappled with worldwide pressures. Mass die-offs came next. The end Ordovician event, the Phanerozoic's second biggest wipeout, wiped out about 85% of ocean dwellers. Trilobites took devastating hits. Brachiopods plummeted sharply. Graptolites got hammered. The layered ecosystems that defined Ordovician ocean bottoms fell apart. Their building block organisms vanished due to the chill, shrinking habitats and the chain of breakdowns sparked by the weather turn. Might the ring's shadow have fed into this disaster? Was the stretch of dimmer equatorial sun, spanning decades or centuries, enough to shove the climate over the edge into ice age? The schedule hints at yes. The ring broke apart during the mid to late Ordovician period, its strongest shading likely peaking as its mass and optical thickness reached their height. The Hernand glaciation struck right at the close of the Ordovician, possibly 10 to 15 million years following the ring's complete dispersal. That's a considerable delay. Should the ring have sparked the chill, its influence would have been postponed, channeled via gradual climate feedbacks. The ocean's thermal sluggishness might account for that gap. Vast reserves of heat stored in the sea mean its temperature shifts at a leisurely pace. Prolonged dimming of sunlight at the equator could chill the upper layers fairly swiftly, over decades or centuries. Yet, penetrating that cold into the ocean depths demands far more time. The complete shift in climate from lowered insulation could take millions of years to fully emerge, as the water's total heat slowly adjusts to the altered energy input. Shifts in the carbon cycle add further postponements. Should cooling near the equator disrupt biological output, modify continental erosion speeds, or alter how organic carbon gets sequestered in ocean floor deposits, levels of CO2 in the air would evolve across hundreds of thousands to millions of years. Lower. CO2 would intensify the initial chill from the ring's blockade, pushing the climate toward ice ages, via processes that trailed well after the primary trigger. This idea holds water, yet lacks proof. It could prove impossible to verify. Pinning down climate causes challenges us even for incidents from mere decades back, armed with detailed measurements and advanced simulations. Trying to link events from hundreds of millions of years past, relying on patchy, indirect records and shaky controls on past conditions, pushes science to its edge of reliable insight. All that's left is a narrative aligning with the evidence at hand, clashing with none of it. The ring emerged, blocked equatorial light, scattered across tens of millions of years. Temperatures dropped throughout that span. The drop peaked in full glaciation. That ice age sparked widespread die-offs. The links tying these happenings together stay conjectural, yet credible, intriguing without confirmation. Precisely the sort of theory that upcoming studies could back or debunk with fresh findings. That shadow has faded entirely. The ring vanished 450 million years back. Its final fragments dropped away. Its dimming ended. Equatorial lands and waters now bask in unfiltered sun. The ensuing chill, tied to the ring or just happening alongside, remade the world, closed out the Ordovician, paved the way for rebound in the Quran. Life forms that made it through the freeze couldn't grasp their ordeal. They felt the impacts, sans insight into the roots, adjusted to evolving surroundings without fathoming the powers remolding their realm. A trilabitet, barely hanging on amid dropping temperatures. A brachopod, sifting through seas growing ever icier. A graptolite cluster floating in waters whose heat patterns underwent radical overhaul. Not one could glance skyward, spot the veil, or tie the ring's existence to the weather's upheaval. They endured the era. The majority perished in it. The wipeout showed no pity, wiping out lineages enduring for tens of millions of years. Clans that weathered earlier upheavals, whole niches that appeared as fixed parts of sea life. The balmy, steady oceans of mid-Ordovician yielded to the icy, variable ones of late Ordovician, leaving warmth-loving creatures scant chance to develop the hardiness needed to persist. That eclipse imparts wisdom on a world's vulnerability. Our planet's weather reacts keenly to disruptions, quick to answer tweaks in energy flows that look minor outright, but loom huge against the brink of system balance. A mere few percent drop in solar input, held steady for millions of years and boosted by loops that swelled the starting nudge, enough to ignite ice cover, spark mass death, and overhaul life entirely. The ring arose by chance. No stellar mind set it circling. No intent shaped its birth or fade. One asteroid grazed the Roche limit, cracked apart, looped into path, showered rubble on the ground for 40 million years, then disappeared. The gloom it threw might have chilled Earth sufficiently to terminate a whole era of geology. That's the unpredictability woven into a world's tale. Tiny happenings, a space rock veering a touch nearer than typical, yield vast outcomes via tangled causal threads, too intricate to foresee. too tied to starting states to echo precisely. The Ordovician stood alone. The ring did too. The chill, regardless of whether the ring played a role, stood out as one of a kind. Nowhere else in Earth's timeline does a comparable episode emerge. Still, the underlying processes remain broadly applicable. Shadows chill exposed areas. Such cooling sparks feedback loops. Those loops intensify early disruptions. Once critical tipping points are breached, climate regimes can flip abruptly. These dynamics hold true for the Ordovician as much as for today, for a ringed world or one heating up due to intensified greenhouse gases. The shadow descended, temperatures plummeted, and ice advanced. With the ice's arrival, 85% of ocean species couldn't withstand the aftermath. The Ordovician era was drawing to a close, the balmy, inundated planet, featuring layered ecosystems, massive hunters, and trilobite-laden ocean beds, was crumbling into a realm of greater cold, severity, and intolerance. The most devastating mass die-off since the Cambrian was underway. Gondwana inched southward. This supercontinent had been shifting for tens of millions of years, propelled by plate tectonics at speeds of mere centimeters annually, unnoticed by any creature amid the creep, yet evident only across vast geological spans. In the early Ordovician, Gondwana spanned southern tropical and temperate belts, its edges bathed in warm waters, its heart mostly drowned under shallow equatorial seas. By the late Ordovician, the movement had positioned a large chunk of it atop the South Pole. Continental land at the poles alters the equation dramatically. Seas defy freezing. Water boasts immense heat retention, sustaining warmth through dark polar nights and damping wild temperature swings. A world with open polar waters stays fairly temperate, its poles free of ice or blanketed just by temporary sea frost that thaws annually. But a planet bearing land at the poles fosters enduring ice caps, year-round glaciers, and expansive sheets that thicken in chillier times and hold firm against warming. Gondwana supplied the foundation for such ice buildup. The South Pole, once an expanse of open sea through much of the Ordovician, now formed solid terrain. Winter snows accumulated without fully vanishing in summer. Season by season, layers piled up, packing old flakes into solid ice, spawning glaciers that crept from elevated terrains and sheets that blanketed millions of square kilometers in time. The Hernantian glaciation was now in motion. Dubbed for the Ordovician's closing phase, it endured briefly on a geological scale, maybe a few 100,000 years, or up to 2 million, but wrought profound havoc. Ice accumulation rivaled or surpassed today's Antarctic volumes. Global sea levels sank 70 to 100 meters as moisture locked into frozen forms. Shores pulled back. Vast inland seas that had swamped land masses receded. Creatures tuned to steady seafloor life confronted swift habitat upheavals. The die-off progressed in two distinct surges. This nuance is key. The late Ordovician mass extinction, often shortened to LOME in studies, wasn't one unified disaster, but a paired assault. Separate extinction episodes spaced by hundreds of thousands of years, perhaps, each targeting distinct life forms. Together, they triggered the Phanerozoic's second-worst plunge in biological variety. The initial surge aligned with the ice advance. As glaciers swelled across Gondwana, oceans shallowed, air grew colder, and current flows reconfigured. Warm water denizens in near-shore zones saw their homes vanish. Equatorial life, reliant on consistent warmth, hit lethal cold snaps. Shelf dwellers in submerged lowlands got marooned as lands resurfaced. Their watery worlds turned abruptly to dry ground in an eye blink of deep time. Graptolites took heavy hits right away. These floating drifters, which had exploded in variety over the Ordovician, lost countless families in that opening wave. Graptolite variety tumbled sharply, from over 100 kinds in certain areas to under 20. The holdouts were mostly cold-adapted types, originating from polar fringes and able to handle the chill that doomed their tropical kin. Brachiopods waned, yet held on. Certain lineages vanished, especially those bound to balmy, shallow setups. Others endured, tweaking to the drop in heat or relocating to pockets of viable terrain. Those remnants would surge back in the Silurian, reclaiming shelves amid rising seas and easing climes. Trilobites endured ruinous blows. Many families blinked out in the first wave, their numbers plummeting from Ordovician highs to the reduced levels that defined them for the Paleozoic's remainder. Trilobites were already on a downward trajectory since the mid-Ordovician, pressured by rival arthropods, hunted by cephalopods and eurypterids, and disrupted by shifts in community structures amid broader ecological shifts. Yet the onset of glaciation hastened their collapse dramatically. Following the late Ordovician mass extinction, these ancient arthropods would cease to command the seas as they once did. Cephalopods endured severe setbacks as well. The massive orthocones that once dominated Ordovician waters vanished nearly completely. Endoceras camarascias and its kin faded from the fossil archives entirely. Their enormous 6-meter shells no longer appeared in post-Ordovician layers. The position of top oceanic hunters would later pass to successors like Devonian sharks or Mesozoic marine reptiles, though none of the Ordovician behemoths left heirs able to rival their scale or supremacy. That initial extinction surge wiped out roughly 61% of marine genera, marking it as a significant mass die-off on its own. The ensuing second surge elevated it to true catastrophe. In the interval separating the two waves, environments showed partial rebound. Glaciers pulled back modestly, oceans swelled with higher sea levels, and climates grew warmer. Over this short respite, maybe 200,000 years or even more, certain life forms began reclaiming lost territories, while ecosystems started tentative restructurings, hinting at revival. But this upturn halted abruptly. The follow-up pulse struck right as the Ice Age concluded. Vast ice caps disintegrated swiftly, dumping their freshwater loads back into the seas. Floodwaters surged across newly exposed continental margins. Heat built up, especially in equatorial zones where the prior chill had hit hardest. The very dynamics fueling the first event flipped during the second, ensnaring survivors. Those that had endured the freeze by evolving cold-hardy traits now confronted scorching reversal. Creatures that migrated toward poles to dodge dying tropics suddenly saw their sanctuaries overheat past endurance. First-wave holdouts proved ill-suited to the rebound, exposed to the exact mechanisms dissolving the ice. Oxygen shortages spread through the seas. With melting ice and climbing warmth, waters layered more distinctly. Hot surface layers capped frigid depths, curbing upwelling and hindering air's oxygen from reaching below. Seafloor zones turned hypoxic, then fully anoxic in spots. Starved of any free oxygen, bottom dwellers and near-bottom assemblages asphyxiated. Those that had fled to profundal Chile refugees during the initial crisis discovered such havens now deadly traps. Geological carbon isotope shifts record these suffocating episodes. Sediments from oxygen-poor settings built up with organic matter, low in the heavier carbon-13 isotope. Such signals peak amid the second die-off phase, signaling broad deoxygenation, sluggish ocean currents, and habitats, crumbling not from frost but the thaw's aftermath. Together, the pulses proved ruinous. 85% of sea life perished. Whole food web rolls evaporated. Layered filter feeder setups defining Ordovician bottoms broke apart. Reef constructors crumbled. 50 million years of gradual evolutionary buildup got slashed in under 1 million years of turmoil. The coal targeted selectively. Deep-sea dwellers struggled, cornered in dead zones without escape. Equatorial forms took heavy hits, outpaced by swift thermal swings. Narrowly adapted specialists dropped faster than versatile generalists. Species relying on drifting larvae for breeding, tied to stable seas, succumbed more than direct brooders. A few lineages dodged the worst. Bivalve mollusks, clams, and kin outlasted many peers, their sediment-burrowing habit shielding them from turbulent surface waters. Snails endured, via their wanderlust and adaptable diets, seizing fresh opportunities amid flux. Select echinoderm clades rode out the storm and later bloomed, claiming spots left by fallen rivals. What remained was a stripped-down sea. The Silurian era dawned poorer in variety than the Ordovician's heyday, with sparser food webs and looser-knit assemblages. Rebuilding demanded eons, fresh evolutionary bursts gradually replenishing numbers. Yet the unique mix of life forms defining the Ordovician vanished, supplanted by novel ensembles. Debates persist over the late Ordovician mass extinction's finer triggers, but glaciation stands as the undeniable core. Its alignment with events is simply too exact. The shifts in the environment align too closely with the behavior of ice sheets to be mere chance. This pattern of two distinct pulses, extinctions hitting during both the cooling and subsequent warming, points to swift climate fluctuations as the deadlier force, more so than any fixed hot or cold state. Life forms can adjust to chill or warmth if granted enough time, but they falter when faced with abrupt swings between extremes. It's like a relentless back and forth, with habitats flipping quicker than species can evolve to keep pace. Volcanic outbursts might have played a role as well. Along the edges of Gondwana, arc volcanism ramped up in the late Ordovician, pumping carbon dioxide and various gases into the air. Certain scientists propose that this activity aided in ending the Ice Age by boosting greenhouse effects that heated things up. Conversely, some believe the volcanic outgassing worsened ocean acidification, piling extra pressure on creatures already battered by temperature swings and oxygen dips. Orbital factors behind the glaciation could have intensified the turmoil. Ice masses expand and recede, not in steady progression, but through jerky episodes influenced by Milankovitch cycles, those recurring shifts in Earth's path around the sun and its tilt, which alter how sunlight spreads across the globe. Such ice ages often bring swings, with short thaws breaking up extended freezes. Ocean levels would climb and drop over spans of tens to hundreds of thousands of years. Species attempting to follow these alterations, relocating as habitats moved, encountered ongoing upheavals instead of one isolated disaster. The buildup of strain likely proved more devastating than any single shift. Regardless of the exact triggers, the result stood unmistakable. The Ordovician closed amid disaster. An era of unparalleled marine blooming in Earth's annals, wrapped up with one of history's major ocean die-offs. The contrast runs deep. The globe had fostered a burst of variety that the loam wiped away. 50 million years of evolutionary flourishing unraveled in mere moments through climate upheavals too harsh for life to endure. The frost has thawed. Those glaciers that blanketed late Ordovician Gondwana have vanished. Their remnants lie strewn over landmasses, now wandered thousands of kilometers from the polar origins of the ice. Tillites, sediments compacted from glacial debris, trace the reach of those ice fields, embedded with pebbles and stones gouged by the grind of advancing glaciers. The surrounding grit consists of fine rock powder, crushed under the immense pressure of flowing ice. Today, you can find such tillites in South Africa's Cederberg Formation, in Morocco's Anti-Atlas Mountains, and in Bolivia's Candelaria Formation. The ice imprinted its trace on stones that rest today in balmy subtropical or tropical zones, distant from any poles. They stand as evidence of landscapes long gone and weather patterns scrubbed clean by 443 million years. The stones hold memories beyond the grasp of the life they entombed. The frost marched forward, waters pulled back, chills deepened, and then, before any acclimation could take hold, the ice dissolved. Floods surged in, heats blazed, and oxygen starvation rippled across seas, scarcely rebounding from the initial blow. No alert, no pause, no chance to develop the resilience needed for endurance. 85% perished. Their remnants delineate the divide, that slender rock stratum parting Ordovician from Silurian, the final traces that pin down the loam. Beyond it, the buried records shift. Sparser, the remnants of a calamity that remolded the biosphere. The Ordovician had stood unparalleled. 42 million years of balmy climes, swamped land masses, and sea life exploding in ways unseen before or after. Waters brimmed with trilobites and cephalopods, suspension feeders stacking layered habitats, creatures probing every niche for sustenance in the deep. The heavens once bore a luminous ring, a glow lost to time. Land masses welcomed pioneers, flora and arthropods probing the divide of sea and sky. It all culminated in frost. That ring's silhouette might have factored in. One element in a web of influences, a nudge that edged the climate toward chill. Or maybe it meant nothing at all. The descent, propelled by plate shifts, orbital rhythms, and the whims of drifting continents. The link intrigues but doesn't confirm. It's the sort of echo that chroniclers note without nailing down the trigger. Undeniable, though. The cold arrived, the wipeout trailed it, and the Ordovician realm endured no more. The chapter closed. The holdout started the grind of rebuilding. Waters would swell once more. Habitats would restructure. Variety would creep back in time. But the Ordovician had passed. The steamy, submerged realm had chilled and drained. A fresh chapter stirred. The oceans fell still. Following the mass extinction, the oceans brimmed with silence, their currents carrying scant motion from diminished populations that occupied a fraction of former habitats. Seafloors once blanketed in trilobites, alive with crinoid thickets and bryozoan expanses, resonant with the bursts of cephalopod propulsion as they pursued prey amid the waves. Those same bottoms had grown barren, their assemblages pared down to bare necessities, biological webs cleansed of ornate features. The enduring species weren't selected for elegance or intricacy. Survival hinged on fortune, resilience, and the sheer luck of bearing attributes that aligned with the rigors of swiftly shifting conditions. Certain forms had thrived commonplace in the Ordovician, while others eked out existence in overlooked zones or profound depths beyond the reach of prevailing life forms. The catastrophe upended the hierarchy, and as stability returned, novel clades seized influence. Brachiopods endured. These bivalved suspension feeders, plentiful across the Ordovician expanse, outlasted the event more effectively than most lineages. Their variety waned sharply, with families vanishing and whole trophic niches erased. Yet sufficient remnants persisted to reclaim the Silurian waters. Brachiopods held sway over seabeds for roughly 200 million more years, yielding their supremacy only incrementally to bivalve mollusks during the Mesozoic. The resilient brachiopods were typically broad-spectrum types, enduring across broad climatic spectra, equipped to sieve nutrients from either balmy or chilly seas. They could secure themselves to diverse surfaces or drift freely over yielding muds. Narrow adaptations spelled doom. The equatorial shelf dwellers, those tuned to exact thermal bands or particular beds, faced oblivion. What thrived were the versatile, the resilient sorts that avoided locking into any singular mode of existence. Bivalve mollusks, such as clams, ventured into realms abandoned by brachiopods. Bivalves had dotted the Ordovician scene without fanfare, lacking variety and eclipsed by brachiopod rivals. The die-off altered their fortunes. As brachiopod numbers dropped and vacant niches opened, bivalves launched an evolutionary burst that positioned them as the prevailing bivalved life in today's seas. The shift unfolded gradually. The Silurian stayed a brachiopod domain, though the path forward was clear. Gastropods fared robustly. Snails and kin rode out the crisis with slight attrition. Their locomotion and broad feeding habits enabled them to navigate flux. A gastropod might rasp at seaweed, forage carrion, or hunt fellow invertebrates. Such adaptability shone when reliable food sources vanished and seizing fleeting chances turned crucial. Crinoids made it through, albeit with curtailed variety. The grand Ordovician crinoid groves had vanished, supplanted by modest groupings of less varied kinds. The holdouts revived the classic crinoid architecture, the anchored sieving existence that had served well before, and embarked on deliberate expansion, leading to the crinoid blooms of the Silurian and Devonian. Crinoids stayed vital to ocean life for the ensuing 300 million years, fading only in the Mesozoic amid rising numbers of wandering echinoderms like starfish and sea urchins. Graptolites lingered in slimmer ranks, plummeting from over 100 kinds in select Ordovician assemblages to maybe 20 worldwide. The holdouts chiefly hailed from cold water origins. Taxa built to withstand the chill that doomed their warm climate kin. These would branch out quietly in the Silurian, foregoing Ordovician splendor, before a fresh upheaval in the Devonian wiped out the lingering drifters. Trilobites hung on. They had little say in the matter. Extinction unfolds without intent, a mere consequence. The trilobite stalks that bridged the event emerged as faint echoes of their Ordovician forebears. Variety had been slashed without mercy. The ornate thorned variants, colossal hunters, dedicated swimmers, all but eradicated. Left behind were the jacks of all trades, compact builds, straightforward designs that persisted through obscurity. Trilobites lingered another 200 million years. They never reclaimed the throne. Silurian and Devonian trilobites played supporting roles, ubiquitous yet understated, occupying slots without shaping the seascapes. By the Carboniferous, they grew scarce. The Permian, close to the Paleozoic, mopped up the final holdouts, that lineage which had endured for close to 300 million years and observed the Cambrian burst, the Ordovician diversification, and various mass die-offs, at last reached its conclusion. Conodonts, however, made it through. These slender, eel-shaped vertebrates, known for their tooth-like structures that appear frequently in Paleozoic strata, endured the loam and extended into the Silurian, Devonian, Carboniferous, Permian, and Triassic eras, a striking endurance that persisted until the Triassic-Jurassic boundary event about 200 million years ago. Conodonts produced no heirs. They represented an evolutionary cul-de-sac, albeit a thriving one that spanned 300 million years, yet yielded no enduring descendants in the modern world. The plated jawless fishes, known as ostracoderms, hung on in diminished populations. These initial vertebrates, which had begun testing bony plates and protective gear back in the Ordovician, made it through to keep evolving in the Silurian. In time, they would spawn the jawed fishes, the gnathostoms, which went on to rule watery realms ever after. The saga of vertebrates, which started so hesitantly in the Ordovician, carried onward into the Silurian, laying groundwork for explosive expansions that ultimately led to creatures ranging from sharks to humankind. Meanwhile, on terra firma, the landward push kept going. The basic plants that had taken root along Ordovician coastlines held firm, with their spores turning up in Silurian deposits, signaling that the spread of greenery across land masses had outlasted the ocean catastrophe. The early land arthropods, those trailblazers whose footprints marked Ordovician shorelines, pressed on with their shift to a life sustained by air. The Silurian period brought bolder settlement on land, along with richer ground-based life assemblies. It marked the rise of truly land-adapted networks, not just ones straddling water and shore. The rebound unfolded gradually. After a great extinction, species richness doesn't surge back overnight. For millions of years, Silurian oceans stayed less intricate than their Ordovician forerunners. Habitats slowly restructured themselves. Fresh forms arose to claim vacant roles, while enduring lines branched out into open niches. This rebuilding spanned 5 to 10 million years, outlasting the die-off itself and longer than our own species has roamed. A duration that feels eternal to any creature enduring it, yet amounts to just an instant in the vast sweep of Earth's chronicle. In certain respects, the resurgence fell short. Some functional groups never quite regained their footing. The multi-layered filter-feeding setups of the Ordovician, featuring stacked layers of brachiopods, bryozoans, and crinoids, failed to regain that layered sophistication in the Silurian's reformed reefs, which stayed relatively straightforward. The top predator slot, left empty by the massive orthoconic cephalopods, went unoccupied for many millions of years, until later arrivals like eurypterids in the Silurian and placoderms in the Devonian stepped in to claim it. Still, life endured. It invariably does. Even the most devastating mass extinctions, wiping out 90% or more of species, spare some remnants, and those remnants breed, their offspring then spreading out anew. Extinction trims the tree of life, but doesn't topple it. Fresh limbs sprout from the remaining trunks. Expansion chases wipe out. Species variety climbs back to pre-crisis heights, or even surpasses them. The Ordovician holdouts preserved the breakthroughs from that era. filter feeding arrays in stacked three-tiered formations, active hunting by roaming cephalopods, protective plating to fend off growing threats from hunters, the land invasion by flora and arthropods. These advances stuck around, passed into the Silurian, and further, forming core pillars of the ecosystems that define the Paleozoic's remainder. The extinction winnowed for toughness. The life forms that pulled through were those able to handle shifting surroundings, tap diverse food sources, and hold out amid harsh times. Such qualities, adaptability, broad habits, endurance, would get favored again and again across Earth's timeline, as later catastrophes culled narrow experts and boosted hardy remnants ready for upheaval. The rhythm repeated itself. Wipeout, endurance, rebound, spread, then another wipeout. This loop has unfolded 5 times in the Phanerozoic, the major 5 mass extinctions that carve key lines in the geologic record. The Loam ranked as the second. 3 others loomed ahead. The late Devonian die-offs, the Permian-Triassic crisis that almost snuffed out all complex organisms, the Triassic-Jurassic boundary event, and the Cretaceous-Paleogene strike that erased the non-bird dinosaurs. Every such extinction remolded life's sphere. Every comeback birthed fresh wonders. Creatures that emerged into the world after the extinction differed markedly from the ones that ruled beforehand. Tailored to the altered environment, and they constructed new ecological networks, drawing wisdom from the disaster. Extinction molds evolution just as profoundly as adaptation does. The evolutionary tree has been carved by disasters, equally with rivalry and natural selection. Echoes of the Ordovician linger today. Stroll by a contemporary shoreline, and you're treading Ordovician limestone, compressed remnants of brachiopod, crinoid, and bryozoan shells from roughly 500 million years back. The calcium carbonate they drew from ancient oceans has cycled via plate tectonics, eroded from elevated ranges carried by streams, and laid down as sediment on coastlines that arose long after those beings perished. Those basic elements endure. Their shapes have vanished, yet the substance lingers, altered and repositioned, woven into the ceaseless mechanism molding Earth. Heirs of Ordovician survivors navigate today's seas. Nautilus, the last genus of shelled cephalopods, perpetuates the form first crafted by Ordovician nautiloids. Horseshoe crabs, tracing their roots to the Ordovician, lumber across present-day shores with anatomies barely altered over 450 million years. Brachiopods endure in abyssal realms, these vestiges of ancient life holding on in niches of low rivalry, where their outdated traits still function. The vertebrate line, which started modestly in Ordovician waters, armored, jawless fishes sifting organics from coastal shallows, gave rise to all modern fish, every amphibian, reptile, bird, and mammal. Your spine represents an Ordovician breakthrough. The vertebrate framework upholding your bones, shielding your nerves, enabling your brain's intricacy, was honed in those primordial oceans by creatures freshly discovering ossification. The circle is dissolved. The darkness has faded. The frost has thawed. The extinction has ended. Some 443 million years divide us from the Ordovician, a chasm so immense that comprehension demands metaphors, each needing its own clarification. Still, the link holds firm. The Ordovician forged the realm we occupy. Its breakthroughs remain operational. Its enduring offspring thrive. In the Silurian, oceans teem anew. Sea floors welcome initial settlers post-catastrophe. Land plants expand. Arthropods evolve for dry habitats. The resilient ones diversify, probing voids left by the die-off, sparking the expansions that craft the Silurian and Devonian eras. The Ordovician draws to a close. The balmy, inundated seas blanketing vast land masses recede gradually, rebounding from glacial troughs. The luminous arc that spanned tropical heavens has fully dispersed, its remnants plummeted, its gloom banished. Enormous cephalopods prowling the depths are wiped out, their 6-meter casings missing from Silurian strata. Trilobite fields blanketing Ordovician bottoms have disappeared, supplanted by basic assemblages from hardy lines. What endures is recollection. Etched in rock, fossils capture former inhabitants, layers chronicle deposits, isotopes track shifts. The strata recall the Ordovician flawlessly, though not exhaustively, safeguarding clues that diligent Earth scientists unearth and decode, assembling visions of bygone realms from temporal shards. The tale wraps up here. The Ordovician finishes, the Silurian dawns. Those once vibrant, varied, intricate seas now simplify. Rebuilding demands eons. Scores of species multiply into hundreds, then thousands. Food webs reassemble incrementally, niche by niche, tier by tier. The deliberate, steadfast labor life undertakes post-ruin. The hardy carry on as hardy do. They endure, they evolve. They occupy the gaps carved by mass death. They advance the strategies that succeeded. Discard the refinements that faltered. Experiment with fresh pairings that could thrive where prior designs crumbled. You may relax at last. The extinction is past. The frost has yielded. Oceans ascend. Life persists, as it always has and will, while water flows, energy flows, and carbon's bonds endure. The Ordovician imparted truths on variety, on wipeouts, on ecological brittleness and life's tenacity. The mild coastal waters reclaim their domain. Suspension feeders restore their groves. Hunters pursue. Quarry evade. The vast cycle revolves. The pattern repeats. That radiant band illuminated Ordovician heavens across 40 million years. A streak of brilliance forever beyond human sight. A marvel beheld solely by creatures devoid of awe. Darkness swept over the equatorial band, perhaps chilling the planet. Glaciers gripped Gondwana, draining the oceans as music, and fully 85% of all species perished. Yet what endured propels the tale ahead. The Ordovician endures through its lineage, etched in stone as fossils within limestone layers, and in the breakthroughs that etched lasting traits into Earth's living tapestry. That epoch has concluded. The planet pressed onward. From the remnants fresh beginnings arose. Rest easy now. The Ordovician draws to a close. The waters grow still. The remnants are restoring. Moments advance. Existence persists. Good night.